Formulated in the 17th century by Sir Isaac Newton, it reshaped how humanity views motion, space, and the laws of nature. Imagine it as the physics of everyday life. It's why you can throw a ball and predict instinctively where it will land. It's how we can forecast sunrise, calculate the orbit of satellites, and launch rockets into space. At its core, Newtonian mechanics is built on a few remarkably elegant laws that reveal the hidden structure of reality. These laws are so universal that they apply to falling apples and orbiting planets alike. Let's begin with Newton's first law, often called the law of inertia. An object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This idea may sound obvious now, but it was revolutionary in its time. Before Newton, many believed that objects slowed down and stopped simply due to their inherent nature. But Newton showed that motion continues unless something interrupts it. If you were to kick a ball across a perfectly smooth, endless surface with no resistance, no friction, no air drag, it would continue moving forever. In real life, of course, friction eventually stops the ball. But this law shifted how we see force. It's not motion that requires explanation. It's the change in motion that do. Newton's second law gives us the relationship between force, mass, and acceleration. Expressed with the simple formula F6ma force equals mass times acceleration. This law has become one of the most iconic in all of science. The implications are profound. Push a pebble and it moves. Push a boulder with the same force and it hardly budges. The greater the mass, the more force needed to achieve the same acceleration. Engineers use this law to design everything from elevators to racing cars to spacecraft. It's how we calculate the thrust needed to launch a rocket, or determine how a car's mass affects its handling. Then comes Newton's third law. For every action, there is an equal and opposite reaction. It explains why a rocket can launch into the sky. The exhaust gas is pushed down, and the rocket lifts up. It's why, when you push against a wall, the wall pushes back with equal force, even if nothing seems to move. Swimmers push water backward to move forward. Birds push air downward with their wings to stay aloft. This law reveals the hidden symmetries of force and motion in our universe. Perhaps Newton's most awe-inspiring contribution was the universal law of gravitation. It states that every mass attracts every other mass with a force proportional to their product and inversely proportional to the square of the distance between them. This law doesn't just describe why apples fall from trees. It explains why the moon orbits the Earth, why the planets orbit the sun, and why tides rise and fall, double the mass of an object, and its gravitational pull doubles, double the distance, and the force is reduced to a quarter. These precise relationships enabled scientists to calculate the paths of planets and comets, to predict eclipses, and even to understand the behavior of binary stars. Before Newton, the heavens and the earth were considered governed by different rules. The celestial was divine, the terrestrial mundane. Newton shattered that boundary. He showed that the same force pulling an apple downward is what keeps the moon in orbit. In doing so, he unified the cosmos. For the first time in history, the universe was seen as one connected, predictable whole. Newtonian mechanics is where the modern story of physics begins. It's the foundation of classical mechanics, a branch of science that describes the motion of objects under the influence of forces. The influence of Newtonian mechanics didn't stop at physics textbooks. It revolutionized engineering, architecture, transportation, and space exploration. It's how we design bridges that can withstand storms and skyscrapers that sway but don't fall. It's how we map flight paths, build roller coasters, and understand how planets sling spacecraft on interplanetary journeys. NASA still uses Newton's laws to calculate launch trajectories and interplanetary slingshots. Every spacecraft launched into orbit or beyond relies on the calculations rooted in these principles. Even though physics has since evolved, adding the layers of relativity and quantum mechanics, Newtonian mechanics remains essential. For most of our daily experiences and technological needs, it works with astonishing accuracy. It tells us how fast a train will stop, how much stress a bridge can endure, and how a pendulum will swing in different environments. It's the language of motion, from playground swings to planetary paths. Newtonian mechanics gave humanity more than just equations. It gave us a new lens for understanding the world. It showed that the universe isn't a chaotic place of mysterious orbits, but a realm of orderly behavior governed by discoverable laws. It was the birth of the scientific worldview, a shift from superstition to systematic inquiry. In every step we take, every machine we build, every orbit we plot, Newton's insights echo. These timeless laws continue to guide us as we explore not only Earth, but the farthest reaches of the cosmos. They remain a powerful reminder that even the most complex movements of nature can often be described by the ideas elegant enough to fit in a single line of mathematics. And that may be Newton's greatest gift, the knowledge that with observation, logic, and courage, even the forces of the universe can be understood and used to shape our destiny among the stars. Newtonian mechanics, though born in the 17th century, continues to serve as one of the most practical and foundational frameworks in science. It works remarkably well for describing motion and force in our everyday world. We use it to build bridges, play planes, calculate the trajectory of a thrown ball, and send satellites into orbit. But as humanity's curiosity grew, reaching into the vastness of space and the microscopic depths of atoms, scientists discovered its limitations. When we begin to observe objects that travel at the speeds approaching the speed of light, or that exist within the warping pull of extremely massive bodies like black holes, Newton's laws no longer hold up. In such extreme conditions, the classical rules of motion begin to break down. This is where Einstein's theory of relativity enters the scene. And on an even smaller scale, at the atomic and subatomic levels, it's quantum mechanics that takes over. These modern theories don't replace Newtonian mechanics. They expand upon it, stepping in where its boundaries are exceeded. Nevertheless, Newtonian mechanics remains a masterpiece of simplicity and power. It doesn't explain everything, but it explains a great deal with extraordinary precision, especially in the macroscopic world we interact with every day. Engineers, architects, pilots, and astronauts still rely on Newton's principles to ensure safety, predict outcomes, and understand the fundamental forces at play. In many ways, it represents the triumph of clarity. Simple laws governing astonishingly complex behavior. And this clarity laid the foundation for even deeper inquiries into how the universe works. It paved the way for the next great frontier in physics, the study of energy, change, and the flow of heat. In a word, thermodynamics. At its essence, thermodynamics is the science of transformation. It explores how energy moves, changes form, and interacts with matter, from engines and refrigerators to stars, black holes, and even biological cells. Thermodynamics provides the rules for what can happen and what can't in our universe. It's the reason a hot cup of coffee cools over time. It's why your body needs food to stay warm. And it's why we'll never be able to build a machine that runs forever without energy input. To understand thermodynamics, we must explore its 4 fundamental laws, each revealing a layer of how energy behaves in physical systems. Let's begin with what is known as the zeroth law of thermodynamics. Though often overlooked, this law establishes the concept of temperature and thermal equilibrium. Imagine three objects, A, B, and C. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A must also be in equilibrium with C. This principle may sound obvious, but it's the basis for using thermometers. When you place a thermometer into a glass of water, it eventually matches the water's temperature. Thanks to the zeroth law, we can trust that the reading reflects the true thermal state of the liquid. Now let's turn to the first law of thermodynamics, the law of energy conservation. It tells us that energy cannot be created or destroyed. It can only change forms. Push a boulder up a hill, and the energy from your muscles becomes stored as potential energy in the rock. Let it go, and that potential energy transforms into kinetic energy as it rolls downward. Whether it's mechanical energy, heat, or light, the total amount remains constant, just distributed differently. This law places firm boundaries on what's physically possible. It's why you can't get more energy out of a system than you put into it. Consider the internal combustion engine in a car. Gasoline holds chemical energy, which combusts into heat. That heat moves pistons, which in turn moves wheels, but not all the energy becomes motion. Some is as always lost as waste heat, radiating outward, no longer usable. The first law tells us you can change energy's form, but you can't make more of it from nothing. Now we arrive at a more unsettling truth, the second law of thermodynamics. This law introduces the concept of entropy, a measure of disorder or randomness, and it states something profound. In any isolated system, entropy tends to increase over time. Order decays. Imagine a deck of cards, perfectly organized by suit. Shuffle it, and the order dissolves into randomness. Try to restore the exact original order by shuffling again, and you'll likely fail. In fact, it's almost impossible. The same happens in the physical world. Pour cream into coffee. It mixes naturally. But you'll never see it spontaneously separate back into distinct layers. This increase in entropy is what gives time its direction. We call it the arrow of time. Time moves forward because entropy increases. It's also why no machine can be 100% efficient. There will always be waste heat, always be some energy dispersed into less useful forms. This law explains why perpetual motion machines, a fantasy of inventors for centuries, are impossible. You cannot get more out of a system than what nature permits. There is always a cost. Thermodynamics not only governs engines and weather systems, it governs the universe itself. And in the next section, we'll explore the third law of thermodynamics and its eerie relationship with the coldest possible state of matter. Thermodynamics is more than just a branch of physics. It's a philosophy of motion, of limitation, and of change. At its heart, it's the science of energy, how it's stored, how it's transformed, and why it can never be entirely recovered. And one of its most profound laws, the second law, introduces us to a concept that quietly shapes everything we see: entropy. Entropy is a measure of disorder, randomness, or chaos in a system. And according to the second law of thermodynamics, the total entropy of an isolated system can only increase over time. This idea, while simple in theory, has vast implications. Take, for instance, cream poured into coffee. Once stirred, the two substances blend together seamlessly, and it becomes virtually impossible to separate them again. That increase in disorder, from two distinct substances to one chaotic mixture, is entropy in action. It's a natural, irreversible process, and no amount of stirring backward will bring the cream back out. Now think of a hot cup of tea sitting in a cool room. Over time, the heat from the tea escapes into the surrounding air. The tea cools, the room warms, slightly, imperceptibly, and the overall entropy of the system increases. Heat always flows from hot to cold, never the other way around, unless external work is applied. This one-way flow of energy is why perpetual motion machines are forever doomed to remain science fiction. They would require a reversal of entropy, a violation of this most sacred law of nature. And yet, as fundamental as the second law is, thermodynamics has even deeper mysteries to offer. Enter the third law, perhaps the most abstract and difficult to visualize. It tells us that as the temperature of a system approaches absolute zero, that unreachable void of low Kelvin, or minus 273 degrees Celsius, the entropy of the system also approaches a minimum, typically zero. At absolute zero, atomic motion ceases. Particles no longer vibrate. Molecular movement comes to a standstill. It is the theoretical stillness of matter, a place no scientist has ever reached and perhaps never will. But even approaching it reveals strange and wondrous phenomena. Some materials, when cooled near absolute zero, become superconductors. They allow electricity to flow with no resistance, no loss, no friction. It's as if the laws of everyday physics are rewritten in that frozen silence. And yet, even as we chase absolute zero in laboratories, we learn something humbling. As we draw closer and closer to it, the energy required to extract even one more fraction of heat grows exponentially. It becomes harder and harder until the last sliver of warmth seems untouchable. The third law reminds us some frontiers remain forever on the horizon. Thermodynamics isn't just theoretical, it powers our world. Refrigerators, for instance, use compressors and coils to remove heat from inside and expel it outward. It seems to contradict nature, moving heat from cold to warm. But it's only possible because of the input of work, usually electricity. Steam engines, too, were born from thermodynamic principles. Water is heated to create pressurized steam, which pushes pistons or turbines, converting thermal energy into mechanical work. From these engines came the Industrial Revolution, and from that, the modern world. The same laws that govern kettles and engines also guide the stars. In the heart of every star, nuclear fusion transforms matter into radiant energy. Hydrogen atoms fuse into helium, releasing light and heat, but also increasing entropy. As stars age and exhaust their fuel, they evolve, expanding into red giants, collapsing into white dwarfs, or exploding into supernovae that birth neutron stars or black holes. Each transformation is a thermodynamic story of energy, pressure, and entropy. Thermodynamics doesn't just describe machines. It explains why no energy system is 100% efficient. It defines the limits of life, technology, and possibility in biological organisms, in collapsing galaxies, in engines and ice cubes. These laws rule. They remind us that change is inevitable, that energy will always find a way to disperse, that every action carries a cost, not always in dollars, but in the currency of entropy. To live in a thermodynamic universe is to accept these laws as our silent boundaries. But within those boundaries, we innovate, we adapt, we thrive. We harness the flow of energy, designing systems that balance the trade-offs, working within the constraints of what nature allows. Thermodynamics is a quiet truth, a hum beneath the chaos that reveals the symmetry, the sacrifice, and the unstoppable flow of energy through everything that was, everything that is, and everything that will ever be. The tale of electromagnetism begins with a mystery as old as civilization. Long before we had equations, we had awe. Ancient Greeks noticed that amber, when rubbed with fur, could attract feathers, straw, or dust. What they observed was static electricity, a buildup of electric charge caused by friction. This simple experiment held the seeds of a much deeper truth. Today we know that all electric fields originate from charges, and these charges come in two distinct kinds, positive and negative. Opposites attract, likes repel. This attraction and repulsion between charges creates a kind of invisible force field, the electric field. Picture it as the energy around a charged object reaching out in all directions. The stronger the charge, the stronger the field. This is why a simple balloon rubbed against your hair can stick to a wall. The balloon gains charge, and that charge creates a field, a silent influence that reaches across empty space and pulls against the charged molecules on the wall's surface. Electric fields shape the way particles interact, but they are only half the story. The other half comes from motion. Because when charges move, when they float, they create something new, a magnetic field. This was a harder mystery to uncover. In ancient China and Greece, people discovered lodestones, naturally magnetized rocks that could attract iron. But it wasn't until thousands of years later that humans began to understand what magnetism really was. In the 1800s, scientists like André-Marie Ampère and Michael Faraday uncovered a breathtaking truth. Electricity and magnetism were not separate forces. They were deeply, inseparably intertwined. Where there is moving electricity, there is magnetism, and where magnetic fields change, they give rise to electricity. This discovery wasn't just elegant, it was useful. Faraday's greatest contribution was the discovery of electromagnetic induction. He found that when a magnetic field changes near a wire, an electric current is produced. This was no mere theory. Imagine a magnet sliding through a coil of wire. As it moves, it causes electric charges in the wire to shift. This is the principle behind the electric generator, the very engine of modern civilization. The turning turbines in a power plant, whether driven by wind, steam, or water, spin magnets near coils of copper wire, producing the electricity that lights our cities and powers our devices. Without electromagnetic induction, our world would be dark. Faraday gave us the mechanism, but James Clerk Maxwell gave us the language. Maxwell's equations, four deceptively simple statements, described everything. How electric charges create fields, how moving charges create magnetism, and how those fields interact. But they also revealed something deeper. That light itself was an electromagnetic wave, a self-sustaining ripple of electric and magnetic energy, moving through space at exactly 292,458 meters per second, the speed of light. This insight was radical. It meant that the glow of a candle, the warmth of the sun, the signal from a radio tower, and the invisible rays from distant galaxies were all part of the same cosmic symphony. One phenomenon, many frequencies. The electromagnetic spectrum stretches from the longest radio waves to the shortest gamma rays. Each frequency a different note in the music of the universe. Infrared gives us heat. Ultraviolet tans the skin. X-rays peer into bones, and gamma rays burst from supernovae, carrying the violence of the stars. But at the heart of it all is the same simple truth. Electric fields and magnetic fields are two aspects of one unified dance. They shape everything. They power our technology. They guide our compasses. And they even explain why atoms hold together. Every screen you look at, every wire in your home, every message sent across the globe, none of it would exist without the forces of electromagnetism, a force we cannot see, but which we feel in every flicker of light and every pulse of power. It's not just a scientific principle, it's the hidden current beneath our entire way of life. Electromagnetism isn't just a theory. It's the silent architect behind nearly every device you touch, every screen you see, every wire humming behind your walls. At the heart of it all lies a simple principle: the interplay between electric currents and magnetic fields. This elegant interaction gives rise to electric motors, machines that turn electricity into motion. In a motor, electric current flows through tightly wound coils, creating magnetic fields. These fields then interact with permanent magnets, producing a controlled rotation. That spin drives the blades of your way, the wheels of your car, the motor in your washing machine. Without this dance of fields and currents, modern life would come to a standstill. And yet, motors are only the beginning. Consider transformers, not the robots of fiction, but the quiet titans of our power grid. Transformers use Faraday's principle of induction to adjust the voltage of electricity for safe and efficient transport. Before electricity reaches your home, its voltage is stepped up for long distance, then stepped down again so it can safely power your light bulbs and phone chargers. These silent guardians make possible the vast electrical networks that span continents. But the influence of electromagnetism goes deeper still. Dive into the microscopic world, into the very structure of matter, and you'll find electromagnetism at work. Electrons orbit atomic nuclei because of electromagnetic forces. Atoms bind into molecules because these forces dictate attraction and repulsion. Every chemical bond, every reaction, every stable structure, from water to day, owes its existence to this force. Without electromagnetism, chemistry wouldn't exist. Neither would you. And then came the quantum revolution. As quantum mechanics deepened our understanding, electromagnetism revealed a new face, one that flickered and pulsed in the strange world of subatomic particles. In quantum electrodynamics, the electromagnetic force is carried by particles called photons, the very same photons that make up light. Whenever two charged particles interact, they do so by exchanging these photons. This isn't just poetic, it's the literal mechanism by which the universe holds itself together. And what's truly astonishing is the strength of this force. Compared to gravity, the electromagnetic force is almost 36 times stronger. It holds molecules intact. It allows your brain to think, your eyes to see, your heart to beat. In fact, nearly every interaction you experience on a daily basis, from touch to taste to sight, is a consequence of electromagnetic force. It is the most intimate of all the fundamental force. It lives in our skin, our nerves, our breath. And yet, its scope extends outward, to the stars, to the satellites circling our globe, to the very signals that let us speak across oceans. From cell phones to satellites, Wi-Fi to X-rays, it is the backbone of the modern world. Every time you stream a song, read a message, or warm food in a microwave, you are using electromagnetic radiation. And we are just beginning to tap its potential. Quantum computing, magnetic resonance imaging, laser technology, particle accelerators, all rely on its principles. We've built civilizations atop its quiet strength. It bridges the visible and the invisible, the mechanical and the spiritual, the known and the yet to be discovered. Electromagnetism is more than a force. It's a language, a structure, a cosmic script written in fields and particles. It connects the wires in your wall to the motion of electrons in your blood. It reminds us that behind every button we press is a law of nature, unchanged for billions of years, but made useful by human curiosity. And still, the mystery deepens. Because as we push the boundaries of what electromagnetism can do, we uncover new realms, new ways to manipulate light, energy, information, and even the fundamental nature of reality. The future will be shaped by those who master this invisible force, a force that has always been here, carving out the patterns of the cosmos, even before we had the words to describe it. Picture two twins. One remains on Earth, living an ordinary life. The other climbs aboard a spacecraft and races through the cosmos at a speed near the speed of light. When the traveling twin finally returns home, they find something strange. Their sibling on Earth has aged decades, but they themselves have aged only a few years. This is not science fiction. This is the twin paradox, a real consequence of a theory that reshaped our understanding of the universe. Special relativity, first proposed by Albert Einstein in 1911. Special relativity reveals that time and space are not fixed and absolute, but stretch and shift depending on how fast you move. This stretching of time is known as time dilation. As an object approaches the speed of light, time slows down from the perspective of an outside observer. And it isn't just theory. It's been confirmed by real-world experiments. In one such experiment, scientists placed highly accurate atomic clocks on high-speed jets and satellites, then compared them to identical clocks on Earth. The clocks in motion ran slightly slower. Why? Because the universe has a rule. No matter how fast you're moving, the speed of light must always appear the same. To keep this rule intact, time itself must bend. It must slow down for fast-moving observers so that light remains constant in every direction. From each person's own perspective, time feels normal. But when compared, the flow of time is no longer absolute. It depends on motion. And it's not just time that changes, space does too. This brings us to length contraction. Objects moving near light speed appear shortened along the direction of their travel. Imagine watching a spaceship zoom past at incredible speed. To your eyes, it seems compressed, like it's been squeezed front to back. Yet, inside that spaceship, everything feels normal. The crew walks normally. Their surroundings don't appear squashed. But to the outside world, space has adjusted. It bends and contracts to maintain the balance between speed, light, and time. Special relativity also challenges our idea of now. We think of now as universal, but in truth, simultaneity is relative. Two lightning bolts strike opposite ends of a moving train. To someone standing still on the platform, both bolts hit at the same time. But for a person riding the train, one bolt strikes before the other, not because of illusion or delay, but because motion warps how time unfolds. There is no single universal now. Each observer carries their own thread of time, woven differently depending on speed and direction. That's why what is present for one person may already be past or still future for another. And from these revelations comes the most iconic equation in physics, E = mc2. This formula tells us that mass and energy are not separate. They are two forms of the same essence. In this equation, E stands for energy, m for mass, and ce is the speed of light. Because light travels incredibly fast, squaring its speed, it produces an enormous number. So even a small amount of mass can be converted into a vast quantity of energy. This principle underlies both great creation and devastating destruction. Nuclear reactors harness this conversion to power entire cities. Atomic bombs exploit it for unimaginable force. It reminds us that even what seems solid and still, mass, contains a hidden reservoir of energy. And these ideas don't just live in physics textbooks. They shape the devices in your pocket, Take the GPS in your phone. It depends on satellites orbiting Earth, each carrying precise atomic clocks. But because those satellites are moving so fast, their time slows down just a little compared to ours on the ground. If engineers didn't account for that difference, your GPS would send you miles off the course. So every time you navigate to a cafe or track your location, you're relying on Einstein's insight that time is relative. Special relativity even governs the most advanced machines on Earth. In particle accelerators, like the Large Hadron Collider, protons are accelerated to near light speed. As they gain speed, their mass effectively increases. It takes more and more energy to make them go even faster. That's why no object with a mass can ever reach the speed of light, because doing so would require infinite energy. All of this, time dilation, length contraction, the relativity of simultaneity, and mass-energy equivalence, forms a tapestry of truths that stretch our imagination. Einstein's theory shattered the idea of a rigid, clockwork universe. Instead, it revealed a world of flowing time, bending space, and intertwined realities. And the more we test it, the more it holds. 100 years later, special relativity still stands, not just as a mathematical framework, but as a profound reminder. Reality is stranger, more elastic, and far more wondrous than it first appears. The further you go into Einstein's mind, the stranger the universe becomes. Special relativity showed us that time bends, length compresses, and now isn't the same for everyone. But what if gravity, that familiar ever-present pull, isn't really a force at all? What if it's a trick of geometry, a ripple in the fabric of reality itself? Let's begin in an elevator. You're standing still when suddenly the cables snap. For a moment you feel weightless. You're falling, but you don't feel the force of gravity pulling you down. To Einstein, this wasn't just a thought experiment. It was a revelation. What if gravity isn't pulling you down, but rather you're simply moving along the curves of space itself, as naturally as a marble rolls down a sloped surface? This idea became the cornerstone of general relativity, a theory that reshaped how we understand gravity, not as a force, but as the result of curved spacetime. In Newton's world, gravity is an invisible force pulling objects toward one another. But Einstein envisioned something deeper. He saw space and time as part of a single, malleable fabric, what he called spacetime. And massive objects like stars and planets don't just sit in spacetime. They warp it. They create dents, curvatures, and folds. Just as a bowling ball distorts a trampoline, imagine that trampoline. Place a heavy bowling ball at its center and watch how it deforms the surface. Now roll a marble across that surface. It curves naturally toward the ball, not because the ball is pulling it in, but because the space beneath it has changed. That's gravity, according to general relativity. Mass tells spacetime how to bend, and that bent spacetime tells objects how to move. It's not a force. It's the path of least resistance in a universe that curves around every massive thing. This wasn't just poetic, it was precise. Einstein formulated the Einstein field equations, a set of mathematical expressions that describe exactly how mass and energy distort the fabric of the cosmos. They are complex, yet beautiful, revealing how galaxies bend starlight, how black holes slow time, and how gravity itself becomes a dance between geometry and matter. One of the most mind-bending predictions of general relativity is that gravity affects time. The stronger the gravity, the slower time flows. This is known as gravitational time dilation. Stand near a massive object, and your seconds tick more slowly compared to someone far away. It's not a theory, it's measurable. Try this. Imagine wearing two watches, one on your ankle, the other on your wrist. Your ankle is closer to the center of the Earth, so it experiences slightly stronger gravity. And that means the watch at your ankle ticks just a little slower than the one on your wrist. It's a minuscule effect, but real. And in extreme conditions, like near a black hole, the difference becomes dramatic. Time can slow to a crawl. To a distant observer, it nearly stops. Now picture this. Two massive stars spiral toward each other, colliding in a cataclysm of unimaginable energy. Einstein predicted that such events would send ripples through the fabric of space-time, like waves spreading across a pond. These are gravitational waves, disturbances that carry energy through the universe itself. For 100 years, they remained a mystery, their presence suspected but never directly seen, until 2015. That year, scientists at the LIGO Observatory detected a faint ripple, the echo of two black holes colliding over 1 billion light-years away. The instruments had to measure changes smaller than the width of a proton. But the signal was clear. We had heard the universe whisper, and it sounded exactly like Einstein said it would. That discovery changed everything. It gave us a new way to observe the cosmos, not just through light, but through the bending and stretching of space-time itself. And yet, the elegance of general relativity doesn't end in deep space. It guides satellites, navigates GPS systems, and helps us model the expansion of the universe. Without it, we'd be lost, both metaphorically and literally. Through Einstein's insight, we learned that the universe is not a static grid, but a living, breathing fabric, malleable, mysterious, and deeply connected to the mass and motion of everything within it. It shows us that gravity is not a force reaching out through emptiness. It is the bending of the stage beneath our feet, and in that bending, we glimpse a truth more profound than force. A universe guided not by pull, but by curvature. A vast and silent architecture that shapes the movement of stars, the ticking of clocks, and the rhythm of time itself. Gravitational waves. They are not echoes of sound, but of space itself trembling. For over a century, they lived only in the equations of Einstein. Invisible, untouchable, undeniably predicted. But then, we heard them. Two black holes collided, and across 1 billion light-years, space rippled like water struck by a stone. In 2015, the LIGO Observatory detected that ripple, a tiny vibration, a whisper from the cosmos measured in fractions smaller than an atom. Yet that whisper told a profound truth. Einstein had been right again. Gravitational waves aren't science fiction. They are the universe's own voice singing its most violent symphonies. Merging stars, collapsing suns, the birth of black holes. These waves prove that space-time is not just bendable, it can vibrate. It can carry messages. It can resonate with the pulse of creation. And at the heart of these dramatic events lie, perhaps the most mysterious objects in the universe: black holes. Born from the collapse of massive stars, a black hole is the ultimate punctuation mark in the life of matter. It compresses everything, mass, space, even time, into a single point of infinite density, called a singularity. Here, the laws of physics don't just break, they vanish. Surrounding this singularity is the event horizon, a boundary beyond which nothing escapes. Not light, not information, not even time itself. For decades, black holes were theoretical, but in 2019 we saw one. The Event Horizon Telescope captured the first ever image of a black hole's edge. Not the blackness itself, but the glowing ring of matter circling the abyss. It was like photographing the shadow of God. This moment confirmed what Einstein's theory had foretold, that black holes are not imagination. they are real. They are waiting at the edge of physics and philosophy. But relativity isn't just about the stars. Every time you use GPS to find your way, Einstein is helping. Satellites orbiting Earth experience both special and general relativity. Their speed slows time. Their distance from Earth's gravity speeds it up. Without corrections, your GPS would place you miles away from your destination. That's how precise, how everyday relativity has become. It bridges the infinite and the intimate, the black holes above us and the phones in our pockets. But Einstein's masterpiece, as powerful as it is not the final word. There's a place where it crumbles, where curvature breaks into chaos, where the rules of space and time fade into probability and paradox. That place is the quantum realm. At the quantum level, the scale of electrons, quarks, and photons, the universe plays by different rules. Rules that don't make sense to our everyday minds. Particles can be in two places at once. They can appear from nothing, disappear into uncertainty. This is the world of quantum mechanics. Imagine shrinking yourself down past molecules, past atoms, past protons and neutrons, into a realm so small that matter becomes something else entirely. Not solid, not certain, but probable, a place where reality is a blur of possibilities. Here, traditional physics fails. Newton's laws collapse. Even Einstein's gravity starts to unravel. One of the first puzzles that quantum mechanics confronted was the dual nature of light. Is light a wave, or is it a particle? The answer, both. The double-slit experiment proved it. Fire single particles of light at a barrier with two slits, and instead of forming two simple lines, they create an interference pattern, as if each photon interferes with itself. Now block one slit. The pattern disappears. Somehow the act of observing changes the outcome. This single experiment shattered our assumptions. Reality, it seems, depends not just on what is, but on what is seen. That's the quantum world, where particles exist in multiple states until measured, where outcomes are determined only when attention is paid. And here lies the great riddle, the border between Einstein's smooth, curved cosmos and the chaotic flicker of quantum uncertainty. Now imagine this. We fire a beam of light, photon by photon, at a simple screen with two narrow slits. Nothing strange at first, just tiny particles of light heading toward a wall. If only one slit is open. The photons behave like tiny marbles, forming a predictable pattern behind the slit. Just what you'd expect. But if we open both slits, the outcome changes completely. Suddenly, the photons no longer behave like particles, but like waves. They create an interference pattern, bright and dark stripes, as if each photon somehow split in two, passed through both slits at once, and interfered with itself. And it gets even stranger. Fire the photons one at a time, waiting between each shot, and over time, the same interference pattern emerges. Each particle acts as if it knows the slits are open, as if it's aware of all possible paths, and chooses them all. How can this be? How can a single particle behave like a wave? How can it know what's possible, unless reality itself isn't fixed until observed? This is the heart of wave-particle duality, a mystery that extends beyond light. Even electrons, the particles that make up matter itself, show the same strange behavior. They too can form interference patterns. They too can exist in multiple paths until someone looks. At the quantum level, observation creates reality. In the world we know, if we know a car's speed and location, we can predict where it'll be a moment from now. But in quantum mechanics, certainty vanishes. Enter Heisenberg's uncertainty principle. It tells us this. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This isn't a flaw in our tools. It's not a technical issue. It's a feature of reality itself. At the tiniest scales, particles do not have defined positions and speeds until we interact with them. Trying to pin down both is like chasing a shadow through fog. It slips away as soon as we get close. This leads us to something even more bizarre: superposition. Particles don't exist in one state or another. They exist in all possible states at once, until we observe them, and then the wave of possibility collapses into one actual outcome. To help make sense of this, physicist Erwin Schrödinger proposed a now famous thought experiment. Imagine a cat in a sealed box. Inside, a device has a 50-50 chance of releasing a deadly poison. Until we open the box, the cat is not dead or alive. It is both. It exists in a superposition, alive and dead simultaneously, until someone looks. Ridiculous? Yes. And yet, in the quantum world, this logic holds. Electrons have been shown to occupy multiple places at once, only collapsing into a single location when observed. Measurement is not passive. It's active. It shapes the outcome. It chooses the reality. And it gets even stranger. Particles can become entangled. Their properties become linked. Not by space, not by proximity, but by something deeper. Once entangled, if we measure one particle, the other instantly reflects the result, even if it's on the other side of the universe. Einstein called it spooky action at a distance. He didn't like it, but it's real. We've proven it again and again. This phenomenon, quantum entanglement, defies classical understanding. It seems to violate even the speed of light, but it works, and we are learning to use it. Quantum computers don't just use bits of ones and zeros. They use qubits, which can be 1, 0, or both at the same time. This allows them to explore millions of solutions simultaneously, solving problems in moments that would take normal computers years. Entanglement enables quantum encryption, communication so secure that any attempt to intercept it would change the data itself. These aren't just theories. Quantum mechanics powers lasers, MRI machines, and the smartphones in your hand. Every time you send a message, stream a video, or use a GPS, you're leaning on the strange truths of the quantum world. Electrons don't behave like marbles. They tunnel, they teleport, they flicker in and out of states, choosing paths based on probabilities, not certainties. Quantum mechanics doesn't say, this will happen. It says, this might happen with this chance. The universe at its core isn't deterministic. It's probabilistic. You can roll the dice, you can know the odds, but you can never be sure until you look. And when you do, you change everything. Quantum mechanics has shown us something startling. The universe is not what it appears to be. We once thought reality was solid, predictable, and governed by rules that never bent. But in the quantum world, everything we thought we knew begins to fall apart. Particles don't just exist in one place. They occupy many possibilities, floating in a cloud of potential until something or someone looks. This realm invites us to abandon the comfort of certainty and accept a universe that is far stranger than our senses would ever suspect. In this world, superposition allows particles to be in multiple states at once. Uncertainty isn't a fluke, it's a feature of the cosmos. Entanglement defies space. Probability replaces prediction when time and causality begin to wobble. The deeper we go, the more dreamlike it all becomes. And yet, for all its mystery, quantum mechanics works. It works so well it can predict particle behavior with a precision that defies imagination. It is one of the most successful theories in the history of science, verified by thousands of experiments, yet still holding mysteries we can't fully grasp. And so, the journey continues. Physicists are now trying to merge quantum mechanics with Einstein's general relativity, the theory that governs the cosmos at large. But so far the two frameworks refuse to align. One governs the stars, the other the subatomic world. Together, they could unlock the theory of everything, a final equation that explains all of reality. But for now, they remain at odds. Like two masterful poems written in different languages, quantum mechanics encourages us to let go of classical logic, to see the universe not as a machine, but as a vast, shifting tapestry woven from chance, connection, and collapse. At its core, it reveals a cosmos not made of solid objects, but of relationships, probabilities, entangled potentials always on the edge of becoming. Let's now revisit one of its most essential ideas, the uncertainty principle. To understand it, imagine standing in a pitch-black room. A rubber ball bounces around. You can't see it, only hear it strike the walls. You reach out, trying to guess where it might be. But every time you reach, the ball changes direction. It seems to dodge your hand as if it knows. That's what particles do in the quantum world. The uncertainty isn't your fault. It's built into nature. This idea was first proposed in 1900 by Werner Heisenberg. He showed that there is a fundamental limit to what we can know about certain pairs of properties, in particular, position and momentum. The more precisely we measure a particle's location, the less precisely we can know its momentum, and vice versa. This isn't due to bad tools. It's not about precision. It's a law of reality. Before we observe a particle, it doesn't have a fixed position. It exists as a wave of probabilities. Only when we measure it does it collapse into a single outcome. But that collapse comes at a cost. We lose other information. If we trap a particle with incredible accuracy, we erase any knowledge of its speed or direction. This interplay defines the quantum world. Picture an electron, not as a point, but as a fuzzy cloud hovering somewhere around an atom. We can only say, it's likely to be here. We can never say, it's exactly right there and moving like this. In classical physics, better tools solve better problems. But here, no tool can break this limit. It's baked into the mathematics and the fabric of the universe itself. Every act of measurement is also an act of disturbance. To see a particle clearly, we must bounce something off it, usually a photon. But photons carry energy. The more precise we want to be, the more energy we must use. And that energy alters the particle, changing its momentum, its behavior, and possibly its destiny. The more we grasp, the more we change. It's a cosmic paradox. And it's not just philosophical. It has practical consequences. This uncertainty explains why electrons don't orbit atoms like planets around the sun. Instead, they exist in probability clouds surrounding the nucleus, regions where they're likely to be found. It also explains why atoms are stable. Because of this uncertainty, electrons can't simply fall into the nucleus. If they did, their position would be perfectly known. But that would make their momentum infinitely uncertain, which nature doesn't allow. This leads to something amazing. Even at absolute zero, particles still possess energy. This is called zero-point energy, a consequence of uncertainty itself. Nothing can be truly still. There is always a tiny flicker of motion, a shimmer of life in the void. And from this shimmer comes another quantum miracle, quantum tunneling. Particles in the quantum world can do something astonishing. They can pass through barriers they have no energy to overcome. This isn't science fiction, it's a phenomenon known as quantum tunneling. Because of the uncertainty in their position and energy, a particle like an electron might be found on the other side of a barrier, not by going over it, not by going around it, but by going through it, as if the wall was never fully there. It's as if probability itself granted a secret passage. This is not a rare trick. Quantum tunneling is at the heart of the nuclear fusion that powers stars, including our sun. And right now, every time you turn on your computer, your phone, or any digital device, you rely on this principle, because the transistors inside use tunneling effects to function. Quantum mechanics is not just theoretical, it's quietly running the world around us. Still, the uncertainty principle remains a challenge, because it pushes us to question everything we think we know. It says clearly, there is no absolute certainty. In everyday life, we assume cars have exact speeds and locations. We assume the planets move in clean arcs, but at the quantum level, those assumptions dissolve. Particles can be here and there, fast and slow, clear and blurred, all at once. Heisenberg's principle shattered our comfort with well-defined reality, and from it emerged the Copenhagen interpretation, a radical idea in physics. This interpretation tells us something profound. Reality doesn't solidify until it is observed. Before we measure, a particle is a probability cloud, not a fixed thing. Only when we observe does it choose a state. The act of looking becomes a creative act. This sparked philosophical firestorms. Does reality depend on consciousness? Does the observer influence the outcome? Physicists and philosophers are still debating these questions today. The uncertainty principle revealed not just limits in measurement, but a deeper truth about existence itself. The universe, at its core, may be built as much from mystery as from matter. At the smallest scales, certainty is a mirage. And that is not a bug. It is a design of the cosmos. Particles are not solid marbles, they are fields of possibility. They exist as waves of chance until something or someone calls them forth. And from this strange, foggy world emerges one of the most haunting phenomena of all quantum theory: entanglement. To understand it, picture two identical twins separated at birth. One grows up in a noisy, bustling city. The other lives quietly on a distant island. Years pass. They live completely different lives. But whenever one feels something, joy, pain, sorrow, love, the other somehow knows. There is no message sent, no phone call, no letter, just a mysterious connection that defies explanation. This poetic idea captures the spirit of quantum entanglement. Albert Einstein didn't like it. He called it spooky action at a distance, because it violates everything classical physics held sacred. Entanglement happens when two particles, born from the same event, become linked in such a way that their states are forever intertwined. Measure winning, and you instantly know the state of the other, even if they're separated by thousands of light years. No signal travels, no message is sent. It just is. This isn't theoretical. It's been tested in labs around the world, and every test confirms the same thing. Entangled particles act as if they are still one system, even when light years apart. They share a hidden bond, a quantum handshake that never breaks. To see how strange this is, consider a particle's spin. Spin is like a type of rotation. We can measure it as up or down. If two electrons are entangled and we measure one as spin up, the other will instantly be spin down. It doesn't matter how far apart they are. Their fates are entwined. They don't even decide until the moment of measurement. But once one is known, the other snaps into place. They behave like quantum twins, sharing a secret language across the void. But this raises a problem. Einstein's theory of relativity says nothing can move faster than light. And yet, this entangled link seems to transmit information instantly. No delay, no travel time, no warning. It breaks every rule of how we understand space and time. This suggests that quantum reality is not bound by the same laws as classical space. It whispers that at a deeper level, the universe may be non-local, connected not by space, but by entanglement itself. What makes entanglement so haunting is not that particles talk to each other. It's that they never stopped being one. When two particles are entangled, they don't send messages. They don't communicate in any known way. Instead, they share a single unified wave function, a kind of invisible thread woven through both. It's as if they were never really separate in the first place. When you observe one, you don't just learn something about it. You cause the entire system to settle into place. The whole wave function collapses instantly. No matter how far apart the particles may drift, they remain part of the same invisible equation. Einstein, Podolsky, and Rosen weren't comfortable with this. In 1930, they published a paper proposing that quantum mechanics might be incomplete. Their thought experiment, now called the EPR paradox, argued that either something is missing from quantum theory or something truly bizarre is happening. The hypothesis was meant to challenge, to expose a weakness, but instead, it opened a door to something even stranger, the holographic principle. At first, the idea seems unrelated, but deep in the heart of black hole physics, another mystery was unfolding. In the 1970s, Jacob Bekenstein and Stephen Hawking were trying to understand black holes. What they discovered changed everything. They realized that the entropy, the measure of information or disorder, inside a black hole was not tied to its volume, as one might expect, but instead to the area of its event horizon, the surface. This was shocking, because it meant that everything that falls into a black hole, its matter, its energy, even its identity, might be fully represented on its outer boundary. It was as if a three-dimensional story was being written on a two-dimensional wall. From this revelation emerged a stunning possibility. What if the entire universe works the same way? What if our vast, three-dimensional cosmos is really a projection, a shadow, cast from a deeper, flatter reality? This is the heart of the holographic principle. In the 1990s, physicist Leonard Susskind and others advanced the theory. They proposed that our universe, with all its galaxies, stars, and people, could be a hologram, a 3D illusion encoded on a distant surface. Just like a hologram on a credit card carries depth on a flat strip, our reality may be built from something more fundamental and less dimensional than it appears. This idea didn't come from science fiction. It emerged from efforts to unify the laws of nature, to reconcile the rules of the very small with those of the very large. Enter string theory. String theory replaces point-like particles with tiny, vibrating strings, each resonating with its own frequency. In some versions of string theory, the holographic principle is not just possible, it's expected. Space and time, it suggests, are not the final layer of reality. They emerge from a deeper order, an encoded realm with fewer dimensions. Imagine that. Not only are particles uncertain, entangled, and probabilistic, but the very space they move through and the time they travel in might not be fundamental. They could be the result of more basic information we do not yet fully comprehend. If true, the implications are staggering. Every tree, every planet, every thought might be a detailed projection from a lower dimensional field. But does that mean your life is an illusion? Not quite. Just as a hologram looks real and functions like a true object, our universe feels real because the encoded information is incredibly rich. Atoms still bond, light still travels, gravity still pulls. We live in the experience of the projection, and for all intents and purposes, it is our reality. Still, the questions remain. What lies on that cosmic surface? Where is it? And what encoded it all? These questions may lead us to a theory of everything, because the holographic principle offers something no other theory has: a possible bridge between quantum mechanics and general relativity. Two pillars of physics that have long stood apart. By viewing spacetime itself as an emergent phenomenon, the holographic approach hints at a deeper unity. Experiments haven't yet confirmed the principle directly, but hints keep appearing. In 2017, researchers discovered patterns in quantum entanglement that mirrored holographic behavior. It was like glimpsing the edge of a hidden script beneath the visible stage. And tools from holography are now helping physicists study condensed matter systems, black holes, and even the origin of gravity itself. This isn't just an idea. It's a growing framework that may reshape the foundations of how we see the cosmos. So, next time you look at the stars, consider this. What if you're not looking into space, but across it? What if behind all we see, there is a hidden surface, a cosmic canvas, holding the code for everything we think is real? The holographic principle stands among the most radical and mind-bending ideas in modern physics. It doesn't just tweak our understanding, it flips it on its head. It suggests that everything we see, everything we touch, everything we believe to be part of a vast, three-dimensional universe might actually be a projection, a shadow cast from a distant, lower-dimensional surface. Even if it remains a theory, its power lies in how deeply it stretches the boundaries of human thought. Because whether it's ultimately true or not, it forces us to ask, what is reality? What is space? And where does truth really begin? But just when you think it can't get stranger, you step into something even more dizzying: the multiverse. The multiverse theory proposes something astonishing: that our universe is not the only one, that beyond the curtain of space and time, there may be countless others, each with its own laws of physics, its own dimensions, its own stories, perhaps even its own you. What if the Big Bang wasn't a one-time event, but just a single breath in an endless cosmic symphony? This is not just science fiction. It's a serious idea born from the study of quantum mechanics, cosmology, and string theory. To understand where it began, we return to the quantum world. In the early 20th century, scientists like Niels Bohr and Hugh Everett grappled with a strange truth: that before a particle is observed, it doesn't have one state, it has many. This is called superposition. A particle can exist in multiple forms at once, like a coin spinning in mid-air, being both heads and tails until it lands. Hugh Everett asked, what if the coin doesn't land just one way? What if it lands every possible way, each in a separate universe? This was the many worlds interpretation, and it changed everything. It said, every quantum event splits reality. Every choice, every particle shift, every moment of possibility spawns a new world. There is not one timeline. There are infinite timelines, each unfolding beside the others. And you exist in many of them. Each version of you is living a different outcome based on the tiniest turns in the river of possibility. But this is just one kind of multiverse. There are others, each stranger than the last. Let's explore the four leading types. 1. The bubble universes. Eternal inflation. Imagine space as a vast, ever-expanding balloon. As it stretches, small bubbles form within it, each bubble a universe, each one unique, each one sealed from the others. This idea comes from inflation theory, proposed by Alan Guth and Andre Linde. They believed that after the Big Bang, space expanded faster than the speed of light, and this expansion continues, forever spawning new cosmic bubbles. Some might be like ours, some might be utterly alien, with laws of physics we can't begin to imagine. And if this is true, then our universe is just one bubble in an endless foam, too. The many worlds, quantum realities. We touched on this before. Every quantum choice creates a branching point, like a tree with infinite limbs. Every outcome happens somewhere. Every time you choose one road over another, another you walks the opposite path in a parallel universe. These aren't metaphorical. They are literal, according to the theory. An entire cosmos for every variation. A branching multiverses that grows with every breath you take. The Brane multiverse. Higher dimensions. From the world of string theory comes another vision. Our universe, according to this view, is a three-dimensional brane, a floating sheet within a higher dimensional space called the bulk. Other branes may exist alongside ours, just out of reach. They could drift near us unseen. Parallel realities in higher spatial dimensions, and if these branes ever collide, the result could be a Big Bang, a universe born from a cosmic crash. This version of the multiverse suggests our reality is one of many floating membranes, each forming its own cosmos in the vast multidimensional sea. The mathematical multiverse, all that can be. And finally, a bold idea from physicist Max Tegmark. He proposes that all possible mathematical structures exist, and each defines a universe. Every equation, every geometry, every conceivable logic system, if it can exist mathematically, it does exist physically in its own universe. It's as if the cosmos isn't built on matter or energy, but on math itself. Each universe a different page in an infinite library. Each page written in a different language of numbers. Imagine a library with infinite aisles. Each book tells a different story, a different reality. And according to this theory, they are all real, every one of them. Imagine a library with no end. A place where each book holds a different version of reality. In some, the story you're living now is nearly identical. In others, the laws of nature have changed. Stars burn green instead of yellow. Gravity pulls sideways, or perhaps life never arose at all. This is the multiverse. And every book is real. Each page is a universe. Self-contained, self-aware, playing out its own narrative in an infinite cosmic archive. Another image, a still pond, where bubbles rise, float, and vanish. Each bubble, a universe. Some expand and blossom into complexity. Galaxies, stars, consciousness. Others collapse, never forming at all. Some drift beside each other, close but forever separate. This isn't just a poetic metaphor. It may be a solution to one of physics' greatest riddles, the fine-tuning problem. Why is our universe so perfectly calibrated for the emergence of life? Why do the constants of nature, like gravity, the strength of electromagnetic force, or the speed of light, fall into exactly the narrow ranges that allow stars to form, planets to exist, and life to thrive? Change just one of them by a hair, and everything collapses. No stars, no atoms, no you. The multiverse offers an answer. In an infinite sea of universes, all possibilities exist. Some are barren, some are chaotic. Some are too hot, too cold, too fast, or too slow. But a few, by sheer chance, have just the right ingredients. We happen to live in one of those, not because it was chosen, but because only here could someone like you be asking this question. This is known as the Anthropic principle, and it makes the multiverse not just fascinating, but perhaps necessary. Still, there's a problem. How do we prove it? By definition, other universes don't interact with ours. They exist beyond our reach. But some scientists are looking for trace clues hidden in the cosmic background radiation, or in gravitational waves, tiny ripples left behind if the two universes ever brushed heads. Others seek evidence in the quantum world, through experiments that might hint at the validity of the many worlds interpretation. Let's return to that now, because it's here that the multiverse becomes most personal. The many worlds interpretation (AI) is one of the boldest ideas ever proposed in quantum mechanics. It doesn't just say there are other universes. It says they split from ours constantly. Every time a quantum event happens, every time a particle could go this way or that, both outcomes occur. And with each outcome, the universe divides. One version of you turns left, another version turns right. One says yes, the other says no. You may not feel it, but in the space between moments, new worlds are born. To understand MWI, we start with the idea of superposition, where a particle like an electron exists in multiple states at once. It's not spin up or spin down, it's both, until someone observes it. Then suddenly the electron chooses a side. It becomes one thing. It collapses. Or does it? The traditional explanation, called the Copenhagen interpretation, says this collapse is random. The observer forces reality into one path. But MWI disagrees. It says there is no collapse. Both outcomes happen, but in separate realities. You measure spin up, that's one world. In another world, someone else, another you, measures spin down. MWI solves the measurement problem without invoking randomness. Instead of collapsing, the universe branches cleanly, predictably, mathematically. But this raises haunting questions. If every choice splits the world, how many versions of you exist? What are they doing now? Are they happier? Did they make better decisions? Or worse? This isn't just a scientific theory, it's a mirror. A mirror held up to every possibility you didn't live. It makes your life part of something much larger. A tapestry woven from choice, probability, and branching paths. And yet, here you are, in this version, this moment. Your awareness, your story, your experience, unique among infinite selves. So, what does it mean? Maybe it means this: that every moment is sacred. Every decision echoes across realities. Every breath is a point of divergence, where the universe expands again and again to hold the weight of infinite dreams. That is the multiverse, and whether it is real or not, it leaves us with a question that is both humbling and liberating. If you are just one thread in an infinite weave of possible lives, how will you live this one? The traditional view tells us that when something happens, one thing happens. A coin lands, a choice is made, a cat lives or dies. But what about the other possibility? Where does it go? Does it vanish into nothing? Or does it continue somewhere else? This is where the many worlds interpretation MWI enters. First proposed by physicist Hugh Everett in 1900, his idea was bold. The wave function never collapses. Instead, when a quantum event unfolds, all possible outcomes occur, but in separate, branching universes. There is no single result. There are many, all playing out in parallel. Imagine flipping a quantum coin. In our world, it lands heads. But in another, your twin sees tails. You never meet. But you're both real. Now imagine standing at a crossroad. You choose left. But another version of you, right now, chose right and began a different life. You might never know they exist, but they do, somewhere in the fractal web of reality. The implications of MWI are staggering. If every quantum event creates a new universe, then reality is branching constantly, billions of times per second, across every atom, every cell, every breath. There are universes where you chose another partner, or never met them at all, where you stayed home that day and your life was spared, or where a single decision led to something extraordinary. Every possible version of your life is real somewhere. You are not just one you are one of infinite versions. To understand this, let's revisit Schrödinger's cat, the iconic quantum thought experiment. A cat is placed in a sealed box with a mechanism that has a 50% chance of releasing poison. Until the box is opened, the cat is both dead and alive, existing in superposition. According to traditional quantum theory, when you open the box, you collapse reality. The cat becomes either dead or alive. But in many worlds, something far stranger happens. There is no collapse. Instead, you open the box, and the universe splits. In one universe, you see a living cat. In another, you see it dead. Both cats exist. So do both observers, each unaware of the other. This idea may seem like science fiction, but it avoids the messy question: who or what causes reality to collapse? MWI eliminates that problem. There is no special observer, no magical boundary between subject and object. The universe just evolves, naturally, continuously, in all directions at once. It's an elegant solution, but not without controversy. Critics say, if these other universes are inaccessible, how can we ever prove they exist? They call it untestable, unfalsifiable. Some philosophers worry it strips meaning from our choice. If every decision creates new realities, does anything truly matter? But others see it differently. They argue meaning isn't found in what might have been, but in the intensity of being here now. And MWI, rather than denying choice, makes each moment more precious. Because this version of you is a miracle of probability. Among countless possibilities, this thread is the one you're living. This version of you was shaped by choices, chance, timing, and silence. And while others unfold elsewhere, this is the path you walk with full awareness. Many worlds also has deep implications beyond personal identity. In cosmology, it may explain why our universe has just the right conditions for life. In black hole physics, it may offer new paths to solve the information paradox. In quantum computing, the very concept of MWI helps explain how computations can occur across entangled branches of logic. In short, this isn't just about theory. It's about understanding what reality really is. So ask yourself, if every version of you exists somewhere, if every road not taken was still walked by another you, then what will you do with this one? This consciousness, this moment, this fleeting flicker of now before the branches split again? Because perhaps in all the infinite multiverse, what matters most is the story you choose to live right here, in this universe, in this breath. The struggle to unite everything. Quantum gravity, zoom in closer, way closer, down to the level where matter itself dissolves into its most basic forms. Molecules give way to atoms. Atoms dissolve into electrons, protons, and neutrons. And deeper still, into the bizarre, jittery realm of quarks, gluons, and neutrinos. At this depth, the world begins to lose all familiarity. This is the strange domain of quantum mechanics, a place where particles can be waves, where outcomes are probabilities, and where reality exists in a cloud of uncertainty until observed. But now, zoom out, far out, past the trees, the cities, the curvature of the earth, past the stars, the surrounding galaxies, the glowing nebulae. Enter the grand theater of cosmic structure, where gravity reigns supreme, and space itself is not flat, but bent and twisted by mass and energy. Here, Einstein's masterpiece, general relativity, unfolds. Massive objects shape the fabric of the universe. Time stretches near black holes. Light bends around stars. Planets orbit not because they are pulled by invisible strings, but because they follow the curves of warped spacetime. These two visions of the universe, quantum mechanics and general relativity, are our greatest intellectual achievements. Each works astonishingly well, explaining reality on its own scale with unmatched precision. Yet when we try to bring them together, to form one unified theory that can describe everything from the smallest particles to the largest black holes, we hit a wall called quantum gravity. This wall has stood for decades. Quantum gravity is not just a technical fix. It is a quest to explain the universe at its most extreme, a language that can speak to both the whisper of an electron and the roar of a collapsing star. But merging them is like trying to reconcile two ancient dialects, one poetic and probabilistic, the other geometric and deterministic. One governed by the dance of chance, the other by the curve of cosmic law. Let's examine them more closely. In the quantum world, certainty dissolves. Particles don't have definite positions until they are measured. They exist in superpositions, spread out, undefined. Electrons orbit not in neat rings, but in probability clouds. Forces are carried by quanta, particles like photons and gluons, all of it described by fields that shimmer through space, vibrating with potential and possibility. Quantum field theory tells us that particles are simply excitations, tiny ripples in these omnipresent fields. It works beautifully for three of the four fundamental forces: electromagnetism and the strong and weak nuclear forces. But gravity doesn't quite fit. In general relativity, gravity isn't a force at all. It's the shape of spacetime itself. Massive bodies like stars and planets don't emit gravitational particles. They bend the fabric of space around them, and smaller objects simply move through this curve. A planet doesn't orbit the sun because it's being pulled. It orbits because it is falling along the curved geometry created by the sun's mass. So, what happens when you try to bring quantum uncertainty into this curved, flowing fabric? You will run into chaos. At incredibly small scales, called the Planck scale, space and time no longer appear smooth. They become grainy, frothing, turbulent. Spacetime foams with unpredictability. The calm curves of general relativity dissolve, and the neat equations of Einstein break down. You can't use them there. You need something new. This is where quantum gravity must emerge. It is the theory that does not yet exist, a framework that can describe both black holes and atoms, cosmic waves and subatomic jitters. And it matters. Without quantum gravity, we cannot fully understand black holes, the Big Bang, or what truly happens at the center of collapsing stars. But attempts to build it are plagued with problems. One of the biggest is renormalization. In quantum field theory, when we do the math, sometimes we get infinities. To fix this, physicists use clever tricks to cancel out those infinities, leaving us with usable, finite numbers. It works for forces like electromagnetism, but not for gravity. The infinities are too wild, too stubborn. Gravity refuses to be tamed by our usual methods. So we explore new paths. Two of the most prominent are string theory and loop quantum gravity. String theory imagines that particles aren't points. They are tiny, vibrating strings. Different vibrations create different particles. It's elegant, and it includes gravity automatically. But to work, it requires extra dimensions. 10, 11, even more. Dimensions we cannot yet see or prove. Loop quantum gravity, on the other hand, keeps space and time as networks, woven like a fabric of loops. It predicts that space itself is made of tiny, indivisible units. No matter how far you zoom in, you cannot cut space in half forever. Eventually, you reach the quantum of space. Each theory is bold. Each has promise. Each also has profound challenges, both mathematical and philosophical. Some physicists believe the answer lies in an approach no one has thought of yet. Others think quantum gravity may emerge not from equations, but from entirely new ideas about what space, time, and reality even mean. Until then, we search. We build particle colliders. We peer into the hearts of black holes. We simulate universes in code and in mathematics. And we wait for a breakthrough, for a key that will finally unlock the door between the quantum and the cosmic. Because behind that door lies a new understanding, not just of matter and motion, but of existence itself. Let's return to string theory. It doesn't just propose a different shape for particles. It reshapes the entire structure of reality. Instead of treating particles as tiny points, string theory envisions them as minuscule, vibrating strings. Their frequency of vibration determines their identity. One frequency becomes an electron, another a quark, another a photon. But for the math to work, string theory demands something extraordinary. Extra dimensions, not just the familiar 3 dimensions of space and 1 of time, but up to 11 dimensions, curled up and hidden from view, tucked away at scales far smaller than we can currently probe. In this framework, gravity arises from the existence of a hypothetical particle called the graviton, a quantum carrier of the gravitational force. This helps explain why gravity, compared to the other forces, is so incredibly weak. It might be leaking into those hidden dimensions. String theory is elegant. It brings all the fundamental forces together: gravity, electromagnetism, and the nuclear force, under a single mathematical umbrella. There's a problem. It remains speculative. Its predictions are difficult, if not currently impossible, to test experimentally. It's beautiful, but beauty isn't evidence. Loop quantum gravity offers a very different path. It's more conservative in scope, but just as radical in implication. Instead of extra dimensions, it proposes something simpler, yet equally profound: that space and time themselves are quantized, that the fabric of reality isn't smooth, but composed of tiny, discrete loops, woven together like a cosmic tapestry. These loops exist at the Planck scale, so small that even our most powerful instruments can't yet detect them. In this view, space cannot be divided infinitely. It has a fundamental grain. Loop quantum gravity manages to sidestep some of the infinities that plague traditional attempts to quantize gravity. It avoids the contradictions, but like string theory, it remains incomplete. And so unverified by direct observation. Despite their differences, both theories aim at the same destination: to reveal the nature of space, time, and gravity at their most fundamental level. And both may still be missing a piece of the puzzle. But why does this puzzle matter so much? Because it goes beyond physics. It forces us to confront a deeper mystery. Why does the universe even allow us to ask these questions at all? This brings us to the Anthropic principle. At first glance, it seems simple, even obvious. It asks, why does the universe appear so perfectly tuned for life? Why are the laws of nature, the constants of physics, and the initial conditions of the cosmos just right to permit life? And not just any life, but conscious, reflective beings like us. Look closer, and the question becomes stranger, more unsettling. If you tweak the strength of gravity just a bit, no galaxies form. Change the mass of the electron slightly, and the atoms become unstable. Alter the rate of expansion after the Big Bang, and the universe either collapses too soon or expands so fast that no structure forms at all. So how is it that everything is set just right? Imagine a cosmic roulette wheel, a vast wheel with trillions of tiny slots, each representing a different universe with its own set of physical laws and constants. Now imagine the wheel spins and lands precisely on the one slot that permits life. Was that luck? Or is there something deeper at work? The anthropic principle offers two main interpretations, one weak and one strong. The weak anthropic principle, WEP, is modest. It simply states, we observe a universe compatible with life, because only in such a universe could observers exist. It's not a solution, but a filter. It says, of course the universe allows life, because otherwise we wouldn't be here to notice it. It's a kind of cosmic tautology. You find yourself on Earth in the habitable zone, because if Earth weren't habitable, you wouldn't be asking the question. It doesn't explain why the universe is the way it is, but it reminds us that we're seeing it through the narrow lens of survivable conditions. The strong anthropic principle SAP goes further. It suggests that the universe must allow life, that life is not a lucky byproduct, but an inherent feature. Some versions even imply that consciousness plays a central role in shaping or determining the structure of the universe. This raises deeper, more controversial ideas. Is the universe fine-tuned for life? Or does life somehow bring the universe into being? Some physicists avoid the strong version, fearing it borders on metaphysics. But others, especially in the realm of quantum mechanics and cosmology, take it seriously. The anthropic principle also plays a key role in discussions of the multiverse. The idea that our universe is just one of countless others, each with different laws, constants, and properties. If there are infinite universes, it's not surprising that one of them happens to support life, and that's the one we're in. Still, this doesn't feel like a satisfying answer. It replaces mystery with vastness, but offers little understanding, because whether by chance, design, or necessity, the universe we inhabit is strangely accommodating. It allows galaxies to form, stars to burn, molecules to bond, consciousness to arise, and reflection like this to take place. So we return to the deeper question. Is meaning something built into the cosmos, or something we impose upon it? We're not done yet. There is more to explore. Because even as we try to unify gravity and quantum mechanics, to understand the constants and the force, there remains one thing science still struggles to define: the self. Our role as observers shapes everything we see. That may sound obvious, but it's a fundamental truth of reality. We don't observe the full spectrum of what could be. We only experience what can be. Conditions compatible with our existence. That's the core of the weak anthropic principle. It reminds us that our perspective is necessarily filtered. Our universe must support life, or else we wouldn't be here to wonder about it. But what if there's more? What if this universe doesn't just allow life, but is somehow compelled to produce it? This is the core of the strong anthropic principle, and it takes the conversation to an entirely different level. According to this idea, the universe is not a random collection of physical constants. It's not the result of cosmic luck. Instead, it must possess the precise conditions needed for life to emerge. In other words, this universe didn't happen to support consciousness. It was destined to. This viewpoint opens the door to a teleological understanding of existence, one that sees purpose, or at least direction, woven into the laws of nature. Proponents of the strong anthropic principle suggest something both beautiful and controversial: that life, and perhaps even consciousness, are not just accidents in the cosmic story. They are the main characters, not the side effects of creation, but the purpose of it. From this lens, the universe becomes a kind of mirror, a system evolving toward self-awareness. And we, its thinking, questioning beings, are how the universe knows itself. This idea isn't new. Philosophers and mystics have whispered it for centuries, that the cosmos and consciousness are inseparable, that intelligence is not an intruder, but a feature. The anthropic principle now intersects with one of the most fascinating theories in modern cosmology: the multiverse. If our universe seems fine-tuned for life, perhaps it's because there are countless others where life is impossible. Universes where gravity is too weak, or the cosmological constant is too strong, where stars never form, or where matter itself never congeals into structure. In an infinite multiverse, with infinite rolls of the cosmic dice, a few universes are bound to land on the winning numbers, life-permitting numbers, and we naturally find ourselves in one of those. Imagine now the roulette wheel again, but instead of one wheel, there are billions, each representing a different universe. Each spin, a new reality. Some produce barren chaos. Others expand and collapse within milliseconds. But a few, just a few, land on the precise configuration of laws, forces, and constants that allow stars to shine, planets to form, and beings to ponder their existence. In this view, our universe isn't the result of luck. It's the result of necessity, the inevitable outcome of infinite possibilities being played out. But not everyone is satisfied with this explanation. The multiverse, for all its elegance, introduces new complexities. It replaces one mystery with an even bigger one. Because how do we prove the existence of other universes? How do we test the unobservable? It becomes an act of faith. Scientific faith, perhaps, but faith nonetheless. And so, the strong anthropic principle continues to whisper. What if this universe wasn't selected by chance, but designed in some deeper way? Not necessarily by a deity, but by some cosmic principle that requires life to emerge. This brings us to the ancient debate: randomness or purpose. Are we a fluke, a statistical hiccup in an uncaring cosmos? Or are we something more, a necessary consequence of the universe unfolding itself toward awareness? In some interpretations, life is not merely permitted, it is inevitable. Consciousness is not an aberration, it is the culmination. There's a growing line of thought that reality and mind are intertwined, that the observer is not passive, but active in the unfolding of the universe. The anthropic principle becomes more than just a physical observation. It becomes a philosophical revelation. It forces us to ask, what is the role of consciousness in shaping reality? Are the laws of physics static or participatory? If the multiverse exists, does each conscious being occupy the branch that aligns with their experience of survival? And if there is only one universe, why is it so welcoming to life, to thought, to wonder, even in its most cautious form? The anthropic principle challenges our assumptions. It reminds us that our presence is not neutral. That observation changes everything, not just in quantum mechanics, but in the deepest architecture of the cosmos. We don't yet have the answers. But in asking these questions, we touch the edge of something ancient, something sacred. We are no longer just stardust with awareness. We are awareness made from stardust, trying to remember the truth it was born from. And now, to dive even deeper, we must confront the next great mystery, the information paradox. Because if information can never be destroyed, what happens when it falls into a black hole? Imagine you burn a letter, a personal one, filled with memories. The paper turns to ash. The ink vanishes in smoke. But the message once written, was it truly erased? This is not just a poetic question. It's at the very heart of one of the most mind-bending mysteries in modern physics, the information paradox. To understand the depth of this paradox, we must first ask, what is information? In physics, information refers to the physical data describing a system's state, a particle's position, momentum, spin, energy, and interactions. With perfect information, you could trace a particle's entire past and predict its future. According to quantum mechanics, information is never truly lost. It may be jumbled, scattered, or hidden, but it remains somewhere in the system. This principle is called unitarity, a foundational idea that guarantees the consistency of quantum theory. But now, enter the black hole, the cosmic monster, a region of space so dense, so powerful that nothing can escape, not even light. At its center lies a singularity, and surrounding it, the event horizon, the point of no return. Now imagine throwing a book into a black hole, not metaphorically, literally. That book contains information, words, ink, fibers, molecules, energy. As it crosses the event horizon, it disappears from our observable universe, gone. Eventually, as physicist Stephen Hawking proposed, that black hole begins to evaporate. It emits Hawking radiation, a faint glow of quantum energy. And over immense spans of time, the black hole shrinks, weakens, and vanishes. Poof. And here's the problem. The radiation escaping from the black hole appears completely random. No trace of the original book. No signature of its pages, its ideas, its essence. All the information seemingly erased from the universe. But that can't be. Not if quantum mechanics is correct. So we arrive at a crossroads. Two sacred pillars of physics in direct contradiction. Quantum mechanics demands that information is conserved. General relativity allows it to vanish without a trace. This is the information paradox, and it has haunted physicists for decades. Stephen Hawking's insight that black holes radiate was revolutionary. It showed that black holes are not eternal prisons. They leak, decay, and disappear. But it also shattered our confidence in information preservation. Hawking radiation does not carry specific signatures. It looks the same whether the black hole swallowed a planet or a paperclip, as if the universe had forgotten what it once knew. To illustrate, imagine burning a jigsaw puzzle. In classical physics, you lose the picture, but the ashes still contain the mass and energy. In quantum physics, you should also be able to reconstruct the pattern. Even in the smoke, the blueprint should remain. But black holes seem to break this law, and on that was unacceptable. Over time, physicists proposed multiple solutions, each bold, each controversial. The first is the holographic principle, proposed by Gerard de Hooft and later expanded by Leonard Susskind. This idea suggests that the information inside a black hole isn't destroyed, but encoded on its surface. Like a hologram, where a two-dimensional film contains three-dimensional data, the event horizon might record everything that falls in compressed, scrambled form. This means the black hole doesn't forget. It hides. Information is projected onto the surface, preserving unitarity without violating relativity. Next comes the firewall hypothesis. This theory breaks with elegance and embraces a violent frontier. It proposes that an energetic wall, a firewall, exists at the event horizon. Anything falling in doesn't drift peacefully toward the singularity. It burns, incinerated at the threshold, shredded by a raw quantum energy. This firewall might somehow record information in a final burst of energy, but there's a price. It shatters our understanding of smooth spacetime. It breaks general relativity, and that makes many physicists uneasy. Another route focuses on quantum entanglement. What if particles that fall into a black hole are entangled with particles outside? Entanglement creates invisible threads, connecting two particles no matter how far apart they are. Some researchers suggest that as Hawking radiation escapes, it's subtly entangled with what was lost. And through this entanglement, information leaks back into the universe, not in a recognizable form, but in a quantum signature woven into the fabric of space itself. Then we come to the boldest bridge yet. ER equals IP, proposed by physicists like Juan Maldacena. This theory links two seemingly unrelated concepts. ER for Einstein-Rosen bridges, commonly known as wormholes. EPR for Einstein-Podolsky-Rosen entanglement. It suggests that entangled particles may actually be connected through tiny, microscopic wormholes. A hidden bridge in spacetime. Could information be escaping not through heat or waves, but through secret tunnels in the fabric of reality? Could black holes be cosmic portals where quantum data travels in unseen ways? These theories, the holographic principle, firewalls, entanglement, and wormholes, are all attempts to reconcile two truths that should not contradict, but do. Each one pushes physics closer to a unified understanding of gravity and quantum law, closer to what some call a theory of everything, but none is fully proven, and the paradox remains. So we are left with questions. Can the universe forget? Is the loss of information a real phenomenon, or just a trick of incomplete understanding? Are black holes vaults with no key, or libraries waiting to be decoded? In this enigma, we confront something deeper than science. A philosophical wound that asks, what happens to meaning when the cosmos erases its memory? And perhaps, just perhaps, the answer is hidden not in stars, but in the language of reality itself. Imagine standing on the threshold of the ultimate unknown, a place where the laws of nature bend, where gravity becomes infinite, and where time itself begins to warp. Now picture this. You step forward out, but instead of drifting into the abyss, you're met with a wall. Not just any wall, a firewall. A searing curtain of pure energy so intense, so unforgiving, it instantly obliterates everything in its path. This is not science fiction. This is the firewall hypothesis, one of the boldest, most unsettling ideas in theoretical physics today. But let's start from the beginning. Black holes, as described by general relativity, are deceptively elegant. From the outside, they're defined by just a few characteristics: mass, spin, and electric charge. What lies inside, beyond the event horizon, is hidden forever from view. And according to Einstein's equations, if you were an astronaut falling into a black hole, you wouldn't feel a thing at the horizon. No warning, no boundary. You would simply drift through, experiencing what physicists call a smooth spacetime. But quantum mechanics tells a different story, a more chaotic, more protective one. At the core of the information paradox is this simple truth: information cannot be lost, not even in a black hole. Every photon, atom, and quantum interaction, every bit of data must go somewhere. Even if the black hole evaporates through Hawking radiation, the universe is supposed to remember. But how? This is where the firewall enters. According to the firewall hypothesis, instead of a seamless journey past the event horizon, an infalling object would be annihilated at a blazing wall of high-energy particles just before it crosses. It never makes it in. Instead, it's shredded, converted into energy, its information released in a violent burst. Before it can be lost forever. Why propose such a terrifying mechanism? Because physicists were desperate to reconcile the two seemingly sacred principles: that no information can be destroyed, and that spacetime remains smooth at the event horizon. But both cannot be true. Either the event horizon is smooth, as Einstein imagined, or it is a death wall, as quantum consistency demands. This theoretical battleground was ignited in 2012 by a paper from physicists Almhiri, Merolf, Polchinski, and Sully, now famously referred to as AMPS. They showed that preserving all the rules of quantum mechanics and relativity would require breaking something, and they chose to break the idea of a peaceful event horizon. That break became the firewall. Let's visualize it. Imagine you're an explorer approaching a vault said to contain the secrets of the cosmos. As you move closer, sensors detect your presence. Suddenly, a blinding wall of lasers erupts, vaporizing you instantly. You never even set foot in the vault, but the system records you, processes you, preserves your data. This is what the firewall would do: convert any object, any information into a form that can be broadcast back into the universe via radiation. A violent safeguard to ensure the cosmic ledger is balanced. But this raises profound questions. Is the universe truly this brutal? Would nature really allow such destruction just to preserve bookkeeping? And what does it mean for our understanding of reality? If the smoothness of space-time, a principle trusted for over a century, is just an illusion, here's where things get even stranger. The firewall doesn't just challenge our intuition about black holes. It shatters a foundational idea known as the equivalence principle. This principle says, if you're falling freely, you won't feel gravity. It's the core of general relativity. It's why astronauts in orbit feel weightless. But if firewalls are real, then a falling astronaut would suddenly not feel weightless at the event horizon. They would be incinerated. And that is a problem. It means one of our greatest physical theories must give way. Either quantum mechanics is wrong, and information can vanish, or general relativity is incomplete, and smooth space-time is a mirage. So far, no one has found a way to save both. And that's why the firewall hypothesis remains so controversial. Some physicists have fought back. They've argued that firewalls are unnecessary, that subtler mechanisms can preserve information without such violence. Some point to quantum entanglement and unsubtle correlations hidden in Hawking radiation. Others revisit the holographic principle, arguing that no firewall is needed if the black hole's surface already stores every detail within. Still, the question remains: if you were to fall into a black hole, would you pass peacefully into the dark as Einstein believed? Or would you be vaporized at the edge, in a final cosmic flare? This is not just academic. This paradox touches the heart of what we believe the universe to be. Is the cosmos kind to explorers, or does it burn the curious to preserve its secrets? The firewall hypothesis forces us to confront the cost of knowledge. It suggests that answers may lie behind locked doors, and that some doors, once touched, might burn you down before you ever enter. In this tension between gravity and quantum law, between smooth horizons and scorching firewalls, lies a deeper truth. And as physicists continue to probe the shadows of black holes, they are not just searching for answers. They are testing the very limits of what it means to know. What if time, The ticking of the clock, the flow of seconds, the rhythm of life itself wasn't fundamental. What if time, as we experience it, is merely an illusion? This is not just a philosophical question. It's the very heart of one of the most profound ideas in physics. An idea called the Wheeler-DeWitt equation, often described as the wave function of the universe. Born from the minds of physicists John Wheeler and Bryce DeWitt in the 1960s, this equation was one of the first bold attempts to unify the towering giants of modern science: quantum mechanics and general relativity. On one side of the cosmic puzzle, we have Einstein's relativity, a theory that explains gravity, space, and the fabric of the universe on grand, majestic scales. It tells us how galaxies spin, how planets orbit, and how black holes warp the space around them. On the other side, we have quantum mechanics, a theory of astonishing precision that governs the microscopic realm: atoms, particles, waves, and uncertainty. It's a world where reality flickers, where particles exist in multiple states at once, and where observation itself can collapse possibilities into one outcome. Each theory reigns supreme in its domain, but when we try to bring them together, to explain a universe that is both vast and granular, both structured and uncertain, they refuse to cooperate. And nowhere is this clash more dramatic than at the edges of reality itself: the Big Bang and the interiors of black holes. These are places where gravity is infinite, where time and space break down, and where the rules of physics, as we know them, cease to function. This is where the Wheeler-DeWitt equation steps in. It dares to describe the entire universe with a single, all-encompassing wave function. But here's the twist. It doesn't contain time, no past, no future, just a vast, timeless canvas of possibility. In this equation, the universe is not something that evolves over time. Instead, it simply is. All of history, every event, every fluctuation of energy, is already encoded in a static, eternal wave. To grasp this, let's revisit a familiar concept: the Schrödinger equation, the foundation of quantum mechanics. The Schrödinger equation describes how a quantum system changes over time. It tells us how a particle's wave function, its range of possible positions, momenta, and energies, evolves from one moment to the next. But the Wheeler-DeWitt equation is different. It removes the notion of time completely. Instead of telling us how the universe changes, it tells us what the universe is in totality. Imagine pausing a movie and viewing every frame at once. No motion, no sequence. Just a single snapshot that somehow contains the story of everything. That's what this equation attempts to capture. It treats the entire cosmos as a single quantum state, not a system that flows through time, but a structure where time is an emergent property, something that arises only under specific conditions when certain parts of the universe are observed. This leads to a radical implication. Time may not be real, at least not in the way we experience it. Instead, what we call time might be a trick of perspective, a phenomenon that emerges from the interactions between subsystems within the universe. In simpler terms, when parts of the universe observe other parts, they create the illusion of change. This illusion gives rise to what we perceive as the arrow of time, the past, the future, and the relentless march of seconds. But behind the curtain, the universe itself remains timeless. And that's the paradox. We live our lives bound to time, aging, evolving, measuring moments. But if the Wheeler-DeWitt equation is correct, then at the most fundamental level, time doesn't flow. It simply doesn't exist. This concept shakes the very core of physics and philosophy. What does it mean to speak of a beginning if time never started? What does it mean to move if there's no before and after? It also raises the possibility that everything that has ever happened and everything that will already exists in the eternal wave function of the cosmos. We are not moving forward. We are unfolding. This perspective changes everything. Causality, entropy, evolution. These may be artifacts of how subsystems interact, not properties of reality itself. And yet, this isn't just an abstract theory. Physicists continue to search for a deeper equation, a quantum theory of gravity that could reveal how space, time, and matter emerge from this deeper, timeless foundation. Some look to loop quantum gravity. Others explore the holographic principle, or theories where space and time are emergent from entangled information. But through it all, the Wheeler-DeWitt equation remains a bold and haunting vision. A mathematical whisper that the story of the universe may not be a drama played out in time, but a single, eternal structure waiting to be understood. So, next time you feel the seconds slipping by, the hours flying past, remember this: you are not just a creature in time. You are part of a universe that may not know time at all. And in that stillness, in that timeless whole, everything that ever was and ever will be is already written, not in a clock, but in the silent, vast wave of being. Time, as we know it, ticks forward without pause, or so we believe. But what if time, that river we float down each day, doesn't actually flow? What if it's not a river at all, but a library? This is the essence of the Wheeler-DeWitt equation, a theory so radical it dares to erase the very notion of time from the canvas of the cosmos. Unlike the familiar equations of motion, this one doesn't include a time variable. It's not concerned with change through seconds or minutes, because in its world, there is no before and no after, just an endless stillness containing every possible state of the universe all at once. This enigma is known in physics as the problem of time, a revelation that at the most fundamental level, time may not be real. It might be something we impose. A lens, a story, not a property of the universe itself, but a way our minds make sense of experience. To understand this, imagine a vast library, but not the one arranged in time. This library holds every possible book, each one a universe, each page a complete moment. The books don't change, they don't age. They exist, complete, timeless, and silent. Only when we open a book and read it from beginning to end, do we feel a flow, a narrative, a past, a present, a future. But the book hasn't changed. Only our reading of it has. This is how the Wheeler-DeWitt equation views reality, as a massive, all-encompassing wave function, describing the universe in its entirety from beginning to end, not in sequence, but as a unified whole. Our experience of time, then, is an illusion, a product of how we observe and interact with the universe from within. It's like watching a film. Every frame already exists. The story is complete. But the projector moves frame by frame, and we perceive a flow. The real is timeless. Only the act of watching creates time. And so we ask, is the universe like this film? Are we simply reading one book from that infinite library, mistaking the turning of pages for the march of time? Physicists using this framework have begun applying the Wheeler-DeWitt equation to cosmology. In doing so, they're not just describing stars or galaxies. They're describing the entire wave function of everything. Some go even further, suggesting that the universe didn't begin with a bang, but with a fluctuation, a spontaneous event in the quantum vacuum, the lowest possible energy state that still brims with infinite potential. In this timeless sea, the universe didn't happen. It emerged, or perhaps simply was. There was no before. There is no after. There is only is. According to this view, what we perceive as evolution, motion, and cause and effect is simply our interpretation of a static, timeless wave function. And yet, this wave function contains everything, from the first atoms to the rise of galaxies, to your own thoughts as you hear these words. All coexist. All are encoded within the same eternal structure. Still, the implications of this are staggering and controversial. How do we interpret a theory that denies the most basic element of human experience? How do we speak of now if all nows are simultaneous? Many physicists and philosophers argue about what this means. Some suggest the universe is a block, a static entity where all past and future events are already laid out, waiting to be perceived. Others insist that time must still play a role, perhaps as an emergent phenomenon within deeper layers of physical law. And so we stand at the edge of understanding, stepping into the paradox. A universe without time may sound cold, alien, unimaginable. But if it's true, it changes everything. It tells us that change, motion, birth, death are merely different facets of a single unbroken reality. It tells us that we are not racing through time. We are swimming in an ocean that never moves. And perhaps, just perhaps, every memory, every future hope, every version of you that has ever existed or will ever exist is already there in the wave. Not lost, not gone, just waiting to be found. At the foundation of everything, from the tiniest particles to the grandest galaxies, lie four fundamental forces. They are the invisible hands shaping matter, motion, and memory. First, there is gravity, the weakest, yet the most far-reaching. It bends the paths of stars, holds planets in orbit, and warps time itself. It is the quiet ruler of the cosmos, a force that binds without touching, always pulling, never pushing. Second, electromagnetism, the force of light and life. It guides the dance of electrons, ignites the glow of stars, and carries your thoughts as electrical signals in your brain. It creates the visible, the audible, and the warmth you feel from the sun. Third, the weak nuclear force, subtle yet essential. It governs radioactive decay, fueling the sun's core, transforming particles and powering life on Earth in ways we rarely perceive. Fourth, the strong nuclear force, the most powerful of them all. It holds the atom's heart together, binding protons and neutrons in an unbreakable embrace. Without it, matter would fall apart. These four forces govern the machinery of the universe, yet they do so from different realms. Gravity, explained by Einstein's general relativity, rules the cosmic stage. The other three, electromagnetism, strong and weak nuclear forces, are explained by the strange and probabilistic world of quantum mechanics. This divide between the very large and the very small has haunted physics for over a century. Our two greatest theories refuse to speak the same language, but some believe there must be a deeper law, a theory of everything, a single unified framework that binds all force, all particles, all dimensions. Einstein believed in such unity. Though he gave us the key to gravity, he spent his final decades searching for a theory that would link it to electromagnetism. He never found it. But his dream lives on. In the 20th century, quantum field theorists, Feynman, Weinberg, and others, managed to unite the electromagnetic, weak, and strong forces into what we now call the Standard Model. But gravity remains the outcast, elusive, stubborn, a force so deeply woven into the fabric of space-time that quantum mechanics can't grasp it. Not yet. And then there is entanglement, a phenomenon so strange, Einstein himself called it spooky action at a distance. Two particles once linked remain connected, even across galaxies. Change one and the other responds instantly. No message sent. No signal passed. Just connection. Einstein rejected this idea. He believed that something was missing, some hidden variables that would one day restore order to the weirdness of quantum mechanics. But he was wrong. In the 1960s, John Bell proved that no hidden variable theory could preserve the idea of local realism. The notion that things exist with definite properties independent of observation, and that no influence travels faster than light. Experiments confirmed it, over and over again. Entanglement is real, and it's not just theory, it's technology. In quantum computing, entangled particles, called qubits, can perform tasks impossible for classical machines. They don't just store a 0 or a 1. They hold both, simultaneously. And when linked through entanglement, they compute as a single entity, solving problems once thought unimaginable. In quantum cryptography, entanglement becomes a guardian. If two people share entangled particles, they can create an encryption key that no eavesdropper can intercept. Try to peek, and the entanglement breaks. The intrusion is revealed. This is the future of secure communication. But it's also a glimpse into the deeper structure of reality. Some physicists now suggest that space itself may emerge from entanglement, that what we call distance or dimension is just a side effect of how deeply particles are connected. Imagine that. Space, time, and geometry aren't fundamental at all, but illusions built from quantum bonds. Entanglement may be the thread that weaves the fabric of the cosmos. And if that's true, then perhaps gravity and the other forces are not separate at all, but different expressions of an underlying unity we have yet to grasp. The dream of a theory of everything is not just a scientific pursuit. It is the modern echo of an ancient longing, to know how all things fit together, to find meaning in the patterns, to glimpse the order hidden behind the veil. We're not there yet, but with each discovery, with every entangled particle, every unified field, every bold theory, we move a little closer to the heart of reality. Entanglement whispers something profound, that existence may be far more unified than we've ever imagined. It suggests that particles are not independent actors on a cosmic stage, but threads in an intricate tapestry, a web of connection that spans the universe. What if the separateness we see is just illusion? What if the foundations of reality are made not of things, but of relationships? Quantum entanglement hints at such unity, not just a bizarre feature of subatomic behavior, but a clue, a signpost pointing towards something deeper. Even if we never fully unravel its secrets, entanglement reminds us that reality isn't just stranger than we think. It's stranger than we can think. As we step deeper into this mystery, another theory awaits, a framework that attempts to explain not just particles, but the very fabric of reality itself. Quantum field theory. Imagine a vast, bustling city. Each building, street, and vehicle seems distinct. But beneath it all, an invisible network pulses. Fiber optics, electricity, radio signals, binding everything into a seamless whole. Quantum field theory, QFT, is like that hidden infrastructure. To QFT, particles aren't tiny marbles floating through empty space. They're ripples, localized vibrations in invisible fields that stretch across the entire universe. In this view, there is no such thing as nothing. Even in the silence of the void, every inch of space teems with invisible fields, restless, vibrant, alive. There is an electron field, a photon field, a field for quarks, for gluons, for every known particle. When we see a particle, what we're really witnessing is a momentary disturbance, a wave that has risen from the calm sea of its field. Think of it like this. Throw a pebble into a still lake. The ripples that spread outward, those are particles. The lake itself, that's the field. According to QFT, these fields are more fundamental than the particles they create. In fact, without the fields, particles couldn't exist at all. And the beauty of it, the fields never disappear, even in the darkest reaches of space. Even in the coldest vacuum, they continue to vibrate, faintly but persistently. This restless energy, always present even in empty space, is called zero-point energy. It's the hum of the universe when everything else goes quiet. Now imagine this. With enough energy, a localized surge in a field can produce a real particle, a wave big enough to be seen. This is how the universe creates, not from nothing, but from fluctuations within these ever-present fields. Each particle's mass, charge, and spin is just an expression of how it moves through its field. No longer solid, but patterned motion, energy folded into form. Quantum field theory has been astonishingly successful. It underpins the standard model of particle physics, our most accurate system for predicting the behavior of matter and forces. It explains 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, each one mediated by force-carrying particles. Photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak. But there's one outlier, one force still defying unification: gravity. In QFT, every force is a field that can be quantized. But gravity, as described by Einstein, is the curvature of space-time itself. How do you quantize space-time? How do you make a field from the very fabric that contains all fields? That is one of the great and unsolved problems in physics. And yet, some believe the key might lie in the mysterious bridges between particles, in entanglement. What if space-time is not fundamental at all, but emerges from entangled quantum fields? What if the distance between things is nothing more than a reflection of how tightly their fields are woven together? This isn't just science. It's philosophy in its highest form. It asks not what the universe is, but how it becomes. If particles are just vibrations and space is just relation, then reality is no longer a set of building blocks. It's a symphony, a resonance, a pattern of interaction. Quantum field theory doesn't just explain particles, it redefines them. It doesn't just tell us what's out there, it reveals how everything arises from invisible potential. We are not made of things, we are made of excitations, temporary peaks in an eternal sea of fields, unique patterns of vibration in an orchestra that never stops playing. And this is the music we are only just beginning to hear. When particles interact, it may seem like a collision, but to quantum field theory, it's more like a conversation. Every force you feel, every reaction in the physical world, is the result of fields speaking to fields. When 2 electrons repel, what's really happening is the electron fields exchanging photons. The electromagnetic field becomes the messenger carrying instructions, invisible yet powerful. Now, imagine this conversation happening in a room that seems empty. But it's not. Even in a vacuum, a place we once thought of as nothingness, the fields are alive. They never sit still. They vibrate, hum, flicker. This activity gives birth to something strange. Virtual particles. They appear from nowhere. Not truly real in the classical sense, but not imaginary either. They flash into existence, linger for a moment, and vanish before we can detect them directly, and yet they leave fingerprints. Virtual particles are not just theoretical decoration. They are the silent intermediaries that allow interactions to occur. They violate the usual conservation laws because they exist only for brief, borrowed moments. Quantum loopholes in time, but their effects are real. Take the Lamb shift, a subtle shift in energy levels of electrons in hydrogen atoms. It's measurable, it's real, and it's caused by the influence of these ghostly virtual particles. Or consider vacuum polarization, where the vacuum itself behaves like a dielectric, slightly altering the electromagnetic field around charged particles. Again, virtual particles at work, flickering in and out, weaving change into the fabric of space. Despite its success with the electromagnetic strong and weak nuclear force, quantum field theory has a blind spot: gravity. Einstein described gravity not as a force, but as the bending of space-time itself. That view is majestic, but incompatible with the quantized world of fields. QFT thrives in the realm of the very small, while gravity rules the vast architecture of the cosmos. Bridging the two, that's the Holy Grail, a theory of everything. Some physicists seek to bring gravity into the quantum realm with a hypothetical particle, the graviton. This elusive carrier of gravitational interaction, if it exists, would make gravity a field like any other, but the equations don't cooperate. Gravity resists quantization. It's as if the cosmos is holding onto one final secret. That's where string theory steps in. It dares to reimagine particles not as points or ripples, but as vibrating strings. Each note a different particle, each vibration a unique force. This elegant idea could unify QFT and general relativity. But for now, it remains an unfinished symphony. Beautiful, unproven, tantalizing. Yet even without gravity fully integrated, quantum field theory has transformed our understanding of what it means to exist. It tells us that particles are not solid, separate things. They are local expressions, ripples, of a vast universal fields. This insight revolutionized not only physics, but technology. Without QFT, there would be no MRI machines, no lasers, no semiconductors. Entire industries, from medicine to computing, stand on the shoulders of vibrating fields. QFT also reshaped how we understand chemistry and biology. Chemical reactions, just interactions of quantum fields, molecular bonding, and an exchange of energy through invisible networks. What looks like matter is movement. What feels solid is organized vibration. And beneath it all, QFT whispers a reminder. Nothing is truly separate. Everything touches everything else. This brings us to one of the most powerful frameworks in all of science, the Standard Model of particle physics. Picture a grand cosmic stage. Every force, every particle, every interaction. A carefully choreographed play. The Standard Model is the script. It assigns roles to each fundamental particle, grouping them into two main families, quarks and leptons. Quarks are the builders of protons and neutrons. The very heart of atoms. They come in 6 flavors: up, down, charm, strange, top, and bottom. You and I were mostly made of up and down quarks. But in the roaring chaos of particle colliders and the high-energy violence of cosmic rays, the stranger flavors appear, briefly, beautifully, then gone. Alongside quarks stand the leptons. Electrons belong here, as do neutrinos. Particles so ghostly, they pass through planets without pause. Then come the force carriers, photons, gluons, and bosons. Each one mediates a different interaction. Like messengers racing between players, they ensure the script unfolds as written. But gravity remains unscripted, a rogue actor waiting for its coup. The Standard Model doesn't answer every question. It doesn't tell us why the universe exists, or what dark matter is, or where consciousness remains. But it tells us this: at the smallest scale, reality is not made of things, but of relationships, symmetries, and vibrations. We are not made of bricks. We are made of music. And the universe, it plays on. Imagine the atom not as a lifeless structure, but as a vibrant performance, a choreography of particles dancing in space. Among them are the leptons, a group that includes the familiar electron and its heavier siblings, the muon and tau. Each one has a shadow, a nearly massless neutrino companion that glides through the universe as if nothing could ever touch it. These ghost particles are among the most elusive in physics. They slip through solid matter as if it were mist. Millions of them pass through your body every second, and you'll never notice. The Standard Model brings order to this invisible realm. It categorizes the most fundamental particles into 3 generations, each heavier and more energetic than the last. Think of them as Lego bricks in different shapes and colors, clicking together to form protons, neutrons, atoms, and eventually, everything you see. But matter alone isn't enough. Just as a structure needs forces to bind its pieces, the universe relies on force-carrying particles to hold it all together. These messengers of nature allow particles to interact, to bond, to change. Let's begin with light, or more precisely, photons. These particles of light are the carriers of electromagnetism. They keep electrons in orbit, transmit the energy in a sunbeam, and spark the glow of a screen when you flip a switch. Now enter the strong nuclear force, a force that acts like cosmic glue, binding protons and neutrons tightly together. Its carriers are the gluons. But unlike photons, gluons don't communicate with every particle. They interact only with quarks, fusing them into the building blocks of atoms. This force is unimaginably strong, but also limited in reach. It works only at tiny distances, just enough to hold the atomic nucleus together despite the repulsion between positively charged protons. Then there's the weak nuclear force, an underappreciated yet vital actor. Its messengers are the U and Z bosons, and their role is the transformation. They allow particles to change their identity. A neutron becomes a proton. An atom decays and releases energy. This is the hidden magic behind radioactive decay and the burning heart of stars like our sun. Without it, hydrogen would never fuse into helium. There would be no light, no warmth, no life. But the true breakthrough in modern physics came in 2012, when scientists at CERN's Large Hadron Collider confirmed the existence of a long-sought entity, the Higgs boson, often called the God particle. The Higgs isn't divine, but it is profound. It interacts with the Higgs field, an invisible ocean hose that fills all of space. As particles move through this field, some encounter resistance, like swimming through syrup. The more resistance they feel, the more mass they acquire. Quarks, for example, drag heavily through the Higgs field. Neutrinos glide through almost untouched. This is why some particles are heavy, while others are feather-light. The Higgs boson itself is the ripple in this field, a fleeting echo of mass being born. Its discovery confirmed a key prediction of the Standard Model: how matter gains weight, how form arises from the formless. And yet, something is missing. For all its elegance, the Standard Model cannot explain gravity. It gives us photons, gluons, W and Z bosons, but no graviton. Gravity, the force that shapes planets, curves galaxies, and sculpts the universe, is a puzzle piece that simply won't fit. Einstein taught us that gravity is not a force, but a bending of space-time itself. Mass curves the fabric of the cosmos, and other masses follow those curves. It's beautiful, geometric, continuous, but it clashes with the quantized, granular world described by the Standard Model. Physicists have theorized a graviton, a quantum particle of gravity, but no one has ever found one. And even if it exists, the math refuses to align. Two great theories, general relativity and quantum mechanics, each brilliant in their own domain, yet they speak different languages. This tension has ignited decades of research into a possible theory of everything, a single framework that unites all forces, all particles, all interactions. But the gaps go even deeper. The Standard Model doesn't account for dark matter, a mysterious form of mass that doesn't emit or absorb light, but exerts gravity. It shapes galaxies, surrounds us, and makes up 20% of the universe. Yet we don't know what it is, nor does it explain dark energy, a force pushing the universe to expand faster and faster. Invisible, powerful, dominant. Dark energy accounts for nearly 70% of all that exists, and we know almost nothing about it. This leaves us with a strange truth. The Standard Model, for all its precision, describes only about 1/4 of the universe. The rest is dark, silent waiting. And so the quest continues, to discover what lies beyond this elegant but incomplete picture, to uncover the threads that connect the known and the unknown, to listen for the next note in the cosmic symphony, and to ask again and again, what else is out there? Neutrinos, once thought to be weightless phantoms, have shown us otherwise. Experiments now reveal that these ghostly particles do possess a whisper of mass. This discovery, while subtle, marks a quiet rebellion against the predictions of the Standard Model. But neutrinos are only the beginning. At the foundation of all atomic structure lies a deeper, stranger truth. A rule so crucial that without it, matter as we know it would collapse into a formless cloud of chaos. This rule is known as the Pauli exclusion principle, named after Wolfgang Pauli, the Austrian physicist who proposed it in 1920. This principle doesn't shout, but it defines the shape of the universe. At its core, it tells us this: no two fermions, particles like electrons, protons, or neutrons, can occupy the same quantum state within a system at the same time. A simple sentence, but its implications stretch across chemistry, physics, and the very stability of matter. Let's bring it down to Earth. Imagine a towering apartment building, with each floor representing an energy level, and each unit a quantum state. Electrons, like tenants, are trying to move in. But there's a strict building code. Each unit can hold only 2 people, and only if they have opposite preferences. In quantum terms, these preferences are called spin, a fundamental intrinsic property of particles. When the building begins to fill, the first tenants occupy the lowest floors, the lowest energy levels, and once a unit has 2 people with opposite spins, one up, one down, it's full. No one else can squeeze in. The next electron must rise to the next available floor. This may sound like a clever metaphor, but it's the very reason atoms don't implode. Electrons cannot all pile into the lowest energy state. Instead, they must distribute themselves across multiple levels. That enforced separation, that stability. This is what makes atoms three-dimensional, what gives them structure, and what prevents the collapse of matter. Without Pauli's rule, all electrons would spiral down into the same ground state, crushing atoms into unimaginably dense points. But instead, they're spaced out, creating the intricate shells and orbitals that give rise to the periodic table. Let's explore this further. Start with hydrogen, the simplest atom. It has 1 electron, no competition. That electron naturally fills the lowest orbital, known as the 1s orbital. Now move to helium. 2 electrons, They both fit in the same orbital, as long as one spins up and the other spins down. This forms a complete pair, a balanced energy state. But when you reach lithium with 3 electrons, a problem arises. The first 2 spots are taken, so the third must climb up to the next floor, the 2's orbital. This cascading structure continues, layer upon layer, with electrons organizing themselves into increasingly complex configurations. Shells, subshells, orbitals, with distinct energy and angular momentum, all emerge from the single restriction that no 2 electrons may occupy the same quantum state. Each electron is defined by a unique set of quantum numbers, which serve as its address in the atom. These numbers describe its energy, its angular momentum, its magnetic orientation, and its spin. And spin, despite the name, has no classical equivalent. It's not the electron spinning like a top. It's an abstract quantum property with only 2 possible values, up or down. When 2 electrons share the same orbital, Pauli's principle mandates that one must spin up, the other spin down. Only then can they cohabitate. This isn't just theoretical. It explains why elements behave the way they do, why they form certain bonds, why metals conduct, why noble gases resist reaction. The entire periodic table, with its strange zigzag of reactivity and stability, arises from this quiet rule. But there's more. The Pauli exclusion principle doesn't just define atoms. It defines matter itself. Consider what happens under extreme pressure, like in the heart of a white dwarf star. There, gravity tries to collapse matter into itself, but Pauli's rule resists. Electrons refuse to be forced into the same state. This resistance becomes a pressure of its own, called degeneracy pressure, and it's strong enough to hold up an entire star against its own weight. Without it, the star would continue collapsing, eventually becoming a black hole. That's how vital this principle is. It's not just about atomic structure. It's the invisible skeleton of matter, the silent law that tells the universe, you may not double occupy this space. In every cell of your body, in every object you touch, this rule is obeyed, without exception. The next time you wonder how it is that you don't fall through your chair, or why atoms don't collapse in on themselves, remember that somewhere, deep in the quantum fabric of reality, Pauli is still enforcing his one rule: no duplicates allowed. Solid matter may seem simple: tables, rocks, your own hands. But beneath that solidity lies a silent principle holding it all together. One law, one restriction. And without it, everything would dissolve into chaos. That law is the Pauli exclusion principle, and its reach goes far beyond atoms. It governs stars. It governs structure. It governs reality. Let's look deeper. When a star dies, a massive one, far beyond our sun, it often leaves behind a collapsed core. If it's not large enough to become a black hole, it becomes something else. A white dwarf. This is not a quiet ember. It's a cosmic paradox, a dense ball of degenerate matter, often no larger than Earth, but with the mass of the sun. You might ask, how can it stay intact? Why doesn't it just collapse into itself? The answer lies in the Pauli exclusion principle. Even here, in this crushed remnant, electrons refuse to share the same quantum state. This refusal creates a new kind of force: electron degeneracy pressure, a pressure born not from motion or heat, but from identity, from individuality. It is this silent resistance that holds the white dwarf together, balancing the inward crush of gravity with a rule born in the quantum world. And if the collapse continues, if gravity still wins, we reach a more extreme state, the neutron star. Here, electrons are forced into protons, creating neutrons. Now, the Pauli principle applies not to electrons, but to neutrons themselves, and once again it prevents total collapse. Even in the death of stars, this principle whispers, no two alike, no two the same. But this law doesn't just govern the cosmos, it governs chemistry, life, water, breath. Take the water molecule, H2O. Two hydrogen atoms bond with a single oxygen atom. But why this way? Why not three hydrogens, or five? Because the outer shell of oxygen has room for only two more electrons, and only if they spin in opposite directions. This tiny rule of spin dictates the shape of the water molecule. A rule that begins in the quantum realm, creates the geometry of your cells, your blood, your oceans. Shared electrons must align in harmony. One spin up, one spin down. Pauli's principle ensures balance, ensures bond, ensures life. And as atoms grow larger, with more electrons, more shells, more complexity, the principle scales. It commands order. Electrons fill orbitals in a precise sequence. The Aufbau principle guides the path, but it is Pauli's law that sets the rules. Each electron must have a unique quantum identity, energy level, orbital shape, orientation, and spin. From this sequence arises the periodic table, a map of elemental behavior. Why does sodium explode in water? Why is gold so stable? Why is carbon the backbone of life? Because electrons obey Pauli's law. Even in the realm of quantum computing, this principle echoes. Quantum bits, qubits, can exist in superposition, holding both 0 and 1 at the same time. They seem to defy binary logic. But even here, they must respect exclusion. Certain quantum states are forbidden, not by choice, but by law. Engineers working with qubits must design around this principle, using it not as a limitation, but as a framework, a silent architecture of behavior. The Pauli exclusion principle, in essence, defines the architecture of reality. It explains why matter has structure, why you can't walk through walls, why stars shine and then die in stages, why each atom has its own identity. It stabilizes the universe. Without it, the building blocks of matter would pile on top of one another, collapsing into a singularity. Structureless, indistinct. This rule, proposed nearly a century ago, reaches into every layer of existence, atoms, structures, you. Even in a world where uncertainty is king, where particles blink in and out of existence, where measurement itself alters reality, there remains this one solid rule. No two identical fermions can occupy the same state. It is nature's cosmic seating chart, ensuring space, ensuring distinction, ensuring harmony. Next time you drink a glass of water or gaze up at the stars, remember, you exist because particles refuse to be the same. Because in the quantum heart of matter, identity is sacred. And Pauli's quiet law keeps the universe from becoming a blur of sameness, order born from refusal, structure born from exclusion. That is the power of this invisible law. A singularity, a place so dense, so compressed that space and time themselves fold inward, like paper crushed to a pinprick. It's not just mass collapsing. It's the known laws of physics breaking down. And surrounding this point of collapse is an invisible line, the event horizon, a cosmic boundary, a one-way gate. Once crossed, there is no turning back. Imagine a river, a canoe drifting downstream. Far from the waterfall, you can paddle easily, escape the current. But as you draw closer, the pull grows stronger. Eventually, you'll reach a point where no amount of effort can save you from being pulled over the edge. That irreversible line? That's the event horizon, a threshold where gravity becomes fate. Everything, light, matter, energy, that passes this point is destined to fall inward toward the singularity. But in 1974, Stephen Hawking changed everything. He proposed a heresy in the Temple of Physics. Black holes aren't completely black. They glow, they radiate. Not brightly, not with heat or light as we know it, but with a strange, faint shimmer born not from fire, but from quantum magic. This was the birth of Hawking radiation. To understand it, you must abandon classical logic, because in quantum mechanics, even a vacuum, absolute nothingness, isn't truly empty. The vacuum writhes with energy, giving birth to virtual particles, pairs of matter and antimatter, that appear and annihilate so quickly we can barely say they existed. But near the event horizon, something surreal occurs. If one of these virtual particles forms just at the edge, just at that razor-thin line, it's possible for one particle to fall in while the other escapes. The one that escapes becomes real, free. It carries away a sliver of energy, a tiny atoll from the black hole's mass. The one that falls in, it carries negative energy from the outside perspective, and slowly, invisibly, the black hole begins to shrink. Imagine a dance floor. Pairs of dancers spinning briefly, then vanishing. But if one is pulled off the floor, into the abyss, the other remains, a solo figure continuing the rhythm. The dance floor loses energy. The crowd thins. Eventually, if enough pairs are separated, the dance ends. The black hole, that ravenous mouth of spacetime, evaporates. Not quickly, not loudly, but slowly. Over billions of trillions of years. A black hole the size of our sun would take longer than the current age of the universe to fully vanish. But tiny black holes, born in the early universe or possibly created in high-energy environments, they could evaporate now, suddenly, violently, with a final burst of radiation, a ghostly echo of their final breath. This idea sent shockwaves through physics, because it raised a terrifying question. If a black hole vanishes, what happens to everything it swallowed? Every particle, every book, every data bit, every person that ever crossed its horizon. Is that information lost forever? Quantum mechanics says, no. Information must be preserved. But general relativity says, inside the black hole, it disappears. And so arose the black hole information paradox, a battle between two of physics' most sacred pillars, two theories, two truths. At what? Hawking's genius wasn't just in proposing this paradox. It was in redefining what black holes are. He showed that they have temperature, they have entropy, they radiate like any other thermodynamic system. And curiously, a black hole's entropy isn't based on its volume, but on the surface area of its event horizon. This discovery, that the informational content of a black hole scales with its surface, not its interior, was revolutionary. It hinted at something deeper, that maybe space itself is not as it seems, that the universe, at its most fundamental level, might be holographic, with information encoded on surfaces, not volumes. From this insight, a new frontier opened. Quantum gravity, a desperate effort to reconcile general relativity with quantum mechanics, to unify the grand dance of stars with the twitching foam of the quantum vacuum. Black holes, once feared as endpoints, became laboratories of insight, mysteries to be unraveled, teachers of hidden truths. Hawking's radiation was faint, but its implications were blinding. It said, nothing is truly permanent. Even the darkest voids can fade. Even the devourers of stars must one day give something back. And that light, that ghost of a vanished dancer, might be the universe whispering its most profound secret. Even in the silence of gravity, quantum whispers still echo. From the vast silence of spacetime to the flickering heartbeat of quantum fields, we are beginning to sense a hidden harmony, a subtle code woven through the universe itself. Hawking radiation was one clue. It connected the immense pull of black holes with the tiniest fluctuations in the quantum vacuum. It showed us that gravity and quantum physics were not strangers, but perhaps notes in the same unseen symphony. Now we arrive at one of the boldest theories humanity has ever conceived: string theory. Its ambition: to weave together the vast and the small, the strong and the subtle, into one elegant tapestry. To begin, we must revisit the two great pillars of modern physics. On one side, general relativity, Einstein's sweeping theory of gravity, describing planets, galaxies, and the curve of spacetime itself. On the other, quantum mechanics, a wild and precise framework governing the behavior of atoms, photons, and particles smaller than imagination. Each is astonishingly successful. Each describes its domain with breathtaking accuracy. But together, they clash. Try to merge them to describe what happens at the center of a black hole or the first moment after the Big Bang, and the math breaks. Infinities explode. Logic shatters. Something is missing. That's where string theory comes in. It dares to suggest that particles are not particles at all. They are strings. Tiny, vibrating filaments of energy, far smaller than atoms, smaller than anything we can currently measure. Each string is like a musical note. Its frequency, its vibration determines its identity. One vibration might create an electron, another a quark, another still a photon. What we once thought of as separate particles may be nothing more than different melodies played on the same cosmic instrument. Imagine a violin. Its strings can produce many sounds, soft or sharp, low or high. So too, the strings of reality may produce all the fundamental particles, each with its own unique tune. But string theory doesn't just describe matter. It dares to include gravity itself. When physicists worked through the math, they found something startling. Among the allowed vibrations was one that perfectly matched a theoretical particle called the graviton, a carrier of gravitational force. It was gravity, not as a geometric curve in spacetime, but as a quantum force emerging from a vibrating string. This was revolutionary. For the first time, gravity had a place within the quantum world, and there was more. Because these strings are extended objects, not point-like particles, they don't produce the same jagged infinities when they interact. Their stretching smooths the chaos, makes the math cleaner, and the paradoxes fewer. It was as if the universe had always been humming a song, and we had finally begun to hear the chords. String theory soon earned a new name, a theory of everything. One theory to explain all four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. One framework to describe all matter and energy. One truth to unify the cosmos. But this theory comes with a price. To make the math work, it demands something strange. More dimensions. Not just the familiar 3 of space and 1 of time, but 10, or 11, or more. Dimensions so small, so tightly curled, that we cannot see or touch them. Yet they shape everything. Imagine a garden hose from a distance. It looks like a simple line, but move closer, and you see it has width. It has a curled-up dimension. String theory suggests that all around us are these hidden dimensions, curled in on themselves, unseen but absolutely essential. And in these hidden folds, strings vibrate, they dance, they sing the universe into being. It's a radical idea. It challenges our sense, but it holds a seductive promise that the universe is not made of chaos, but of structure, not randomness, but resonance, not particles, but patterns. We are only beginning to understand what this could mean. Because if string theory is true, then we are not just made of atoms. We are made of music. And the universe? A grand cosmic symphony still playing its first movement. Picture a garden hose lying in the grass. From far away it looks like a line, simple, one-dimensional. But to an ant walking its surface, the hose reveals another reality. The ant can move forward, yes, but it can also walk around the hose's circular edge. To the ant, the world is more than a line. It's a loop, a world wrapped around itself. This is how physicists ask us to think about reality. What we see may not be all there is. We perceive 3 spatial dimensions: length, width, and height, and one flowing river of time. But string theory suggests there are more. Dimensions curled so tightly we can't see or touch them. But they're there, humming quietly behind everything. These hidden dimensions are not empty. They shape the way strings vibrate, dictate their frequencies, and in doing so, determine the particles and forces we observe in nature. It's as if each extra dimension adds a new string to the universe's violin, a new possibility for vibration, a new tone in the cosmic orchestra. But it gets stranger still. At first, there wasn't just one string theory. There were 5 beautiful, elegant mathematical frameworks, but different, incompatible. Then, in the 1990s, something extraordinary happened. Physicists discovered that all 5 string theories were actually faces of a deeper, more unified theory. They called it YM theory. The M stands for many things: mystery, membrane, mother, magic. No one agrees on one definition, but they all agree on this. It's the most profound attempt yet to unify all forces, particles, and dimensions into a single vision of reality. M theory doesn't just include strings. It includes branes, short for membranes. These are multidimensional surfaces, like sheets or bubbles, that can stretch across multiple dimensions. Our entire universe, everything we see and touch, could be one such brane. A cosmic bubble floating in a vast sea of higher dimensional space, known as the bulk. Other branes could be floating nearby. Parallel universes with different laws of physics, different histories, different outcomes. And perhaps, at some distant moment, these branes might collide. Some physicists believe the Big Bang itself may have been such a collision. 2 branes slamming together in a flash of creation. It's bold, it's breathtaking, and it's hard to test. That's one of string theory's great challenges. The strings, the branes, the extra dimensions, they are all so small, so far beyond our instruments, that for now we cannot see them directly. And that's not all. String theory predicts an enormous landscape of possibilities. Some estimates suggest there could be 10 or 500 different solutions. That's a number so vast, it dwarfs imagination. Each solution represents a different universe, each with its own physical laws, its own geometry, its own constants. Finding the one that matches our own universe is like finding one grain of sand on a beach that stretches across eternity. This has led to criticism. Some say string theory is too speculative, too mathematical, too far from observation. But others believe that mathematical beauty itself is a kind of evidence, that the consistency, the symmetry, the elegance point to a deeper truth waiting to be revealed. And in the midst of it all is the poetry. Because if string theory is right, then everything we know, everything we are, is made from music. Tiny vibrations echoing across dimensions. The electron is a note. The photon is a chord. The graviton is the whisper of gravity in a higher realm. The universe is not a machine. It is a symphony. And we are not observers. We are part of the song. Each atom in our bodies a resonance of ancient strings that have been vibrating since the dawn of time. String theory may be hard to test, but it is harder to forget, because it gives us something no other theory dares: a vision of reality as living music, as geometry woven through sound, as the echo of a creation still unfolding. And though we may not yet understand it fully, though many questions remain, string theory reminds us that the answers to the universe's deepest riddles may be found not by building bigger machines, but by listening more closely to the notes already playing beneath the fabric of reality. The universe we see, the stars, the galaxies, the glowing arcs of space, may be only a sliver of a much vaster reality, invisible yet fundamental. That's how string theory introduces its most mind-bending concept: extra dimensions. Not just 3 of space and 1 of time, but 10, maybe 11, woven silently beneath everything, and floating within these hidden depths. Branes, short for membranes, they are surfaces of multiple dimensions. Sheets, ribbons, bubbles, unfolding in a cosmic ocean we call the bulk. Our universe, the entire observable cosmos, could be such a 3-dimensional brain, or 3-brain, a soap bubble suspended in the dark waters of a higher dimensional reality. Everything we know, light, matter, forces, thought, could be trapped on this surface. Imagine being an ant, walking along the skin of a giant soap bubble. You can move in every direction across the surface, but try to leave it, try to escape upward or downward. You can't. You're bound to that skin. The air around you exists, but it's unreachable. So it may be for us. We live, move, and breathe on our cosmic bubble. And the bulk, the space beyond, remains hidden, silent, just beyond the veil. But what is the purpose of these extra dimensions? In string theory, they're not optional. They're essential. The mathematics only works if these hidden dimensions exist. These extra folds of space allow strings to vibrate in more intricate ways, giving birth to the particles and forces we observe. Without them, the symphony would be incomplete. And yet, the most curious mystery of all is gravity. Gravity, the weakest of the 4 fundamental forces, is puzzlingly feeble. A fridge magnet can overpower the gravity of the entire Earth. Why? Some physicists believe gravity might be leaking. That is, unlike light or electromagnetism, gravity isn't confined to our brain. Gravitons, the hypothetical quantum particles of gravity, could be slipping through the cracks, escaping into the bulk. Just as a whisper seeps through a wall, gravity may be spreading out across higher dimensions, diluted in our world, but whole in the realms beyond. And here's where the story takes a stunning turn. If brains can exist, could there be other brains, other universes floating beside ours in the higher dimensional bulk? Imagine our soap bubble drifting through space. Now imagine others. Bubbles beside bubbles, entire universes hovering within microscopic distance. Some might mirror our own. Others could be wildly different, ruled by alien physics, unrecognizable particles, strange forms of time. We cannot see them. We cannot touch them. But they may be real, and sometimes perhaps they might collide. Yes, collide. One theory suggests that the Big Bang itself was not the birth of everything, but the consequence of a cosmic collision. 2 brains crashing together in a higher dimensional sea, releasing the man fury that forged our universe. A spark from beyond dimensions. It's a poetic possibility, one that stretches the imagination and rewrites the story of creation. But for now, it remains a theory. We cannot yet peer into the bulk. We cannot yet see the extra dimensions, but we're trying. At CERN, the Large Hadron Collider smashes particles together at near light speeds. Physicists watch closely, hoping to catch the moment a particle vanishes, leaving behind a mystery. Could it be slipping into another dimension? Gravitational wave detectors like LIGO scan the sky for ripples in spacetime. If those ripples behave strangely, deviating from what Einstein predicted, it could be a sign, a hidden pathway, a whisper of the bulk. These are hints, not yet answers, but they fuel the search. Because if brain theory is true, then we are part of something far greater. Not just a universe, but a multiverse. A layered reality stacked like cosmic hygids, some nearby, others impossibly distant. Our universe is one verse in a longer sum, a single vibration on a string that hums across dimensions. And though the brains may be hidden and the bulk invisible, the implications are clear. We are not the center. We are not the edge. We are one ripple in an ocean of possibility. Reality, as we perceive it, feels smooth, continuous, unbroken. We move through space as though it's a calm sea. We experience time as a steady river. But what if that's an illusion? What if, at the deepest level, space is not smooth, but grainy? What if time doesn't flow, but ticks? This is the daring proposition of loop quantum gravity, or LQG, a rival to string theory, offering its own blueprint for the unification of physics. To understand it, we must first face the fracture in the foundation of modern science. On one side, quantum mechanics, the law of the small. Particles flicker in and out of existence. Probability reigns. Uncertainty is not a bug, but a feature. On the other side, general relativity, Einstein's magnificent vision. Gravity is not a force, but the curvature of spacetime. Planets bend space. Black holes stretch time. Each theory is a towering success, predicting phenomena with stunning precision. But together, they clash. Quantum physics is chaotic. Relativity is smooth. Try to blend them, and the math breaks. Equations diverge. Infinities erupt. Reality, as we know it, refuses to merge. And so, the quest began. Among the voices offering a solution was loop quantum gravity. Its insight is radical. Space and time are not continuous. They are quantized, built from tiny, indivisible bits. Just as matter is made of atoms, so too is space made of loops. Loops. Infinitesimal rings of energy woven together into a cosmic tapestry called a spin network. This network doesn't exist within space. It is space. Every edge, every node, represents a quantum of space itself. And this web isn't static. It evolves. It breathes. As the time progresses, not in a flow but in discrete flickering pulses, the spin network reshapes, transforming into something new, a spin foam, a four-dimensional mesh that represents the unfolding of space and time. In this vision, the universe is not made of substance, but structure, not a stage, but a process. Space doesn't stretch like fabric. It pulses like music. Time doesn't slide like water. It hops, beat by beat, in cosmic rhythm. At the Planck scale, the smallest scale imaginable, there are no straight lines, no curves, no smoothness. Only loops. Only quanta. Only the silent dance of a lattice beyond comprehension. LQG removes the need for extra dimensions. It doesn't require vibrating strings or hidden brains. Instead, it builds reality from simple, elegant geometry. This theory suggests that space itself has volume, and that this volume comes in tiny, irreducible chunks. No point is truly a point. No surface is truly flat. The cosmos is granular, like digital pixels on a cosmic screen. And time is no longer a flowing river, but a series of flickering frames. A movie reel rather than a stream. This changes everything. If LQG is correct, then the Big Bang wasn't a singularity, an infinite point, but the moment when spin networks first ignited, when the fabric of space clicked into place from a quantum flag. Black holes, too, would have no singularity at their core, but a dense knot of quantum loops, redefining what it means to fall into darkness. Even the passage of time may be redefined. In some interpretations, LQG suggests that time is not fundamental, that it's an emergent property arising from the relationships between quantum events. We may be living not in a flow of time, but in a web of change, where before and after are illusions born from entanglement. Yet for all its elegance, LQG is still a theory, a possibility, a whisper in the equations. It has no definitive proof, no smoking gun, no particle to detect. But what it offers is profound. A vision of the universe not as a smooth field, but as a shimmering lattice, where geometry is destiny, and the cosmos is constructed loop by loop. As science peers deeper into the smallest scales, we may one day find that the stage of existence is not continuous, but made of steps. That the dance of creation is not free-flowing, but choreographed in quantum rhythm. Loop quantum gravity invites us to all listen to the silence between seconds, to the gaps between grains of space, and discover perhaps that what lies beneath reality is not substance, but structure. What if the beginning of everything wasn't a beginning at all? What if time did not emerge from a singular explosion, but from a contraction, a heartbeat of the cosmos collapsing and expanding in an eternal rhythm? This is the revelation at the heart of loop quantum gravity. It dares to erase the singularity, that terrifying point of infinite density where time, space, and physics all break down. In classical general relativity, you trace the universe back to the Big Bang, and then you hit a wall, a singularity, an impossible mathematical spike where equations fall apart and knowledge turns to mystery. But loop quantum gravity proposes a gentler truth. There was no singularity. Instead, there was a minimum sub, a threshold, a bounce, a moment when the universe contracted as far as it could go. Then it turned, rebounded, and began to grow again. This is the big bounce. And it changes everything. No longer do we need to imagine a beginning from nothing. Instead, we glimpse a cycle, a universe that breathes. This is made possible because in LQG, space and time are quantized. They are made of loops, woven together like the threads of a cosmic fabric. And like any fabric, they have texture, limits, resistance. These loops act as buffers. No matter how dense matter becomes, no region of space can shrink to infinite smallness. No black hole can collapse into a point. No birth of a universe can truly be singular. This vision, where geometry itself evolves, twists, and reshapes, is one of the most radical ideas in all of physics. We no longer view space as a passive backdrop. We no longer see time as a linear river. Instead, we witness a fluctuating, breathing quantum geometry. A reality where the very shape of space can bend, shift, and pulse in response to quantum forces. This geometry is not continuous. It is probabilistic. It exists as quantum states, defined not by certainty, but by likelihood. Distance becomes fuzzy. Volume becomes fluid. Even motion is redefined. Objects no longer move through space in smooth trajectories. Instead, they jump. They leap from point to point. just as electrons jump between energy levels without ever crossing the space in between. Reality, at its root, is pixelated. The illusion of smoothness is just that, an illusion. And from this pixelated truth, LQG weaves a compelling story. A universe made not of substance, but of structure. Not of flow, but of flicker. By abandoning the idea of smooth, continuous spacetime, loop quantum gravity offers a new way to reconcile the great rift between relativity and quantum mechanics. It doesn't just explain space. It explains the structure of space. It explains why singularities don't form, why the universe could have bounced, why time may be granular, why geometry may be alive. And if this is true, then black holes may not be inescapable prisons of light. They may be transitions, gateways, passages to new configurations of space. The death of a star may be the seed of another cosmic phase. The end may be another beginning. Loop quantum gravity does not yet have the final answers, but it offers a lens through which we may glimpse the hidden architecture of the cosmos. It suggests that beneath the veil of perception, reality is woven from loops, tiny, vibrating, dancing rings of quantum possibility. And these loops, interwoven in ever-evolving patterns, give rise to everything. Time, space, motion, change, and even you too, are made of loops. The breath you take, the thoughts you form, the light that touches your skin, all arise from this invisible, intricate lattice of spinning quantized geometry. If loop quantum gravity is right, then we are not merely in the universe. We are the universe, woven loop by loop, breath by breath, through a process older than time and stranger than dreams. Imagine a garden hose. Viewed from afar, it looks like a single line, but come closer and you notice its curves, its hidden dimension coiled in a circle. This is how physicists describe the secret folds of space, the hidden layers where other dimensions may dwell, tucked away beyond our perception, yet fundamental to the structure of everything. This analogy whispers of string theory, one of the boldest attempts to unify the entire universe under a single law. It suggests that everything we see, particles, forces, fields, are not points, but vibrating strings, tiny loops of energy, each oscillating in unique ways, each vibration forming a different particle, a photon, a quark, an electron, a graviton. These strings don't just move in our familiar dimensions, they require others. Extra dimensions, 6 or more, curled tightly like the inner spirals of a shell. It's an elegant theory, a poetic one that might fussily merge the world of the very small, quantum mechanics, with the world of the very large, general relativity. And in doing so, it might give us something humanity has dreamed of for centuries, a theory of everything. But elegance does not equal evidence. For now, string theory remains a landscape of beautiful mathematics, with few roads leading to provable experiments. Its rival? Loop quantum gravity. Rather than relying on the strings, LQG imagines space-time itself as a fabric of discrete loops, quantized, structured like a cosmic latte. Instead of flowing smoothly, space is woven, stitched together from countless tiny threads. It's a different approach to the same old dream, a universe fully understood from first principles, but neither theory has yet reached the mountaintop. We are still climbing, still reaching, still guessing at what lies beyond the veil of perception, and yet, the pursuit itself is sacred, because the search for a theory of everything is not just about physics. It is about meaning. It is about us. If such a theory is found, will it declare the universe as determined, predictable, a machine of blind causality, or will it unveil a deeper truth, one that includes mystery, consciousness, and will? Are we just witnesses to a cosmic film already written, or participants in its unfolding? The implications ripple out, touching free will, reality, time, and soul. Some believe that the theory, when found, will be simple: a clean universal law, a final equation etched in the fabric of spacetime. Others argue that the universe is inherently wild, messy, beautifully complex, and that no single theory can capture it all. Perhaps reality is not something to be reduced, but something to be embraced. Still, we continue. We explore. We measure. We imagine. Because whether through string theory or loop gravity, or something yet to be born, the journey changes us. Each theory, each attempt, teaches us more about the nature of space, of time, of existence itself. It invites us to marvel at the web we are part of, to see that even our questions are part of the universe's unfolding story. If a theory of everything is ever discovered, it will not merely be a tool for physics. It will be a mirror held up to creation, a reflection of the mind that seeks to understand why the cosmos exists at all. And even if that answer remains out of reach, the longing for it makes us more human. It lifts our eyes to the stars. It keeps our minds open in the face of mystery. It calls to us to see ourselves as part of something vast, and yet somehow intimate. In the end, we may find that the theory was not about things, not about particles, not about dimensions, but about connection, a framework not just of forces and fields, but of meaning, of order woven into chaos, of possibility rising from silence. And that perhaps is the most beautiful theory of all. Picture a tree. It begins as a seed, simple, still, unnoticed. But over time, it grows. It branches. It unfolds into complexity, into beauty, into life. This is how Teilhard de Chardin saw the universe. Not as a static machine, but as a living process, an evolving organism moving towards something great, towards something divine. He called it the Omega Point, a final convergence of all consciousness, all life, all matter, into unity. For Teilhard, evolution wasn't just about biology. It was about the soul, about spirit, about the awakening of the universe to itself. As the cosmos expands, so does its inner light. From chaos to complexity, from matter to mind, from isolated beings to a collective intelligence, a sacred wholeness at the end of time. He imagined this not as a metaphor, but as a destiny, a direction encoded into the fabric of space and time. Just as atoms form molecules, molecules form cells, cells form minds, so too do individual minds form something larger, a field of consciousness emerging through love, through connection, through purpose. In this vision, consciousness is not a side effect. It is the goal, the arrow, the flame, and the Omega Point is its destination. Teilhard saw humanity as the latest blossom on the evolutionary vine, a species with the power to shape the outcome of the cosmic story. He compared our journey to a river winding toward the sea. Along the way, it gathers water, carves canyons, sustains forests, connects everything it touches. So, too, our journey shapes the universe, through thought, through compassion, through the slow unfolding of awareness. But what lies at the ocean's edge? According to Teilhard, it is a singularity not of destruction but of divine union, where all minds, every soul, every whisper of life are drawn together into a radiant point of ultimate consciousness, a cosmic climax, not an ending, but a beginning of a new kind of existence. Imagine the internet, once a scattered web of isolated machines, now a global brain, a place where knowledge is shared in seconds, where people once divided by continents are united by thought. Teilhard saw human consciousness doing the same, evolving from fragmentation to unification, from isolation to communion. And just as the web grows more intelligent with every connection, so too does the universe. The omega point is where all paths converge, where complexity reaches its apex, where evolution itself becomes aware. While rooted in faith, Teilhard's vision resonates with science. Modern cosmology contemplates a universe that may one day collapse into a final singularity, a big crunch, mirroring Teilhard's final convergence. Complexity theory, emergent behavior, the strange order born from chaos, all echo his belief that the universe is not falling apart, but coming together. And then there's consciousness, still a mystery, still an unsolved riddle at the heart of reality. Could it be that the universe awakens through us, that it dreams through our eyes, that every act of kindness, every moment of insight, moves it closer to its omega? Teilhard thought so. He saw God not as distant but as present, guiding evolution from within, not commanding from above, but calling from the future. He believed that as we grow in empathy, in wisdom and unity, we move closer to the divine. The omega point is not a place, it is a pull, a gravitational field of spirit drawing all things upward. It invites us to live differently, to see our lives as sacred threads in a tapestry, to understand that every choice, every word, every act of love echoes in eternity. And in a world of war, division, noise, the omega point reminds us that we are not broken. We are becoming. That despite the darkness, we are on a path toward light. That beyond the suffering, there is a purpose taking form. Teilhard's vision isn't just theological, it is deeply human. It tells us that we matter, that consciousness is not alone, but collective, that our evolution is not just survival, but transcendence, and that in the end, we are not just observers of the universe. We are its voice. The omega point asks us to participate, to awaken, to weave the sacred into the everyday. And if this journey is real, then every step, no matter how small, brings us closer to something timeless, to something eternal, to something that has been waiting for us all along.